let's start that. Oh, it's showing the top. Last time it didn't do that. Okay. So what was last section all about in a nutshell? The last chapter that we covered.
About mechanical waves.
Mechanical waves in particular, there was a certain type of wave we were interested in.
Not longitudinal, or
They were
long
called
waves,
transversal
transversal.
waves. So waves that are transversal, perpendicular to the direction that you're sending the energy.
Yeah.
But in particular, we were basically talking about sending waves down ropes or strings or something like that. And that's pretty much what we were focused on. And so that covers a lot of your phenomena for sending waves through mediums. Another large phenomena is when you send a wave through some sort of fluid. In particular, our atmosphere. So we're now going to be focusing now not on transversal waves, but we're going to be focusing now on longitudinal waves, where the direction the energy is sent is parallel to the way the medium is shifting back and forth. Because ultimately, that's how you send a wave. You get your medium jiggling back and forth, which creates a chain reaction of that wiggling back and forth. Right? So this section is now all about sound. In its broadest sense, what is a sound? It is just a longitudinal wave in some medium. So we're used to sound in the atmosphere, but an earthquake produces a sound through the earth. Now we can't hear the earthquake producing a sound through the earth, but that doesn't mean it's not producing a sound through the earth. So sound is produced through all sorts of mediums. Obviously, the one that we're mostly interested in is the sound produced through air that is audible to our human ears.
okay.
So most of the time that's what we'll be talking about, but everything we're talking about here can be generalized to more than just sound waves that we can hear in our atmosphere. But that will be a large focus. And so the sound waves that we can hear in our atmosphere are going to be sound waves of roughly the frequency range of 20 to 20,000 hertz. That's roughly what the human ear can hear. Remember, 20 to 20,000 hertz, that's going to be your frequency. What's a frequency?
Not fast.
Not fast.
Not fast. It's
How much it does in
That's
1
period.
second?
Yeah, cycles per second.
Cycle
Yeah.
per second.
Or wavelengths per second is another way that we'll also
Wavelengths.
think about it this way.
That's right, wavelength.
So if you look at your wavelength and you multiply it by how many wavelengths per second you get, that will give you your velocity. So that will be one of our most common equations that we use over and over again. Don't have it written right here on the front page, but it's going to be the fact that the velocity is equal to the frequency times lambda,
right.
where f is frequency, lambda is wavelength, and v is your velocity. Okay, so from the last chapter, the wave equation that we used over and over again, we came up with a derivation for this wave equation. Nothing changes now that we're going from parallel to transversal. This equation is still the exact same equation. The only difference now is the y is parallel to the x direction rather than perpendicular to it.
That makes sense.
So y is how much it is shifted from its equilibrium position. X would be the location of that particle's equilibrium position.
Okay.
So where the particle's actual x position will be at some time will be its x position plus its displacement from the x position at whatever time it is that you care about. And now that will give you its actual x position. So this is x position. This is how much it's shifting back and forth from its equilibrium position. And it just so happens now it's shifting back and forth in the same direction as that x rather than perpendicular to it.
Okay.
But still the same equation, still the same math. Good so far?
Yeah.
Okay, partial derivatives. Since we use these a little bit, let's dump it on you one more time. I keep dumping these on you over and over again, trying to get you comfortable with it. So let's do it again. So reminder, definition of a derivative. What's the derivative of f with respect to x? It's the limit as delta x goes to 0 of f of x plus delta x going a little bit in the forward, or getting your height a little bit forward minus your height a little bit backward, and then divided by delta x. I shifted down the equation. We're looking at this.
Yep.
Good so far? Definition of a derivative?
Yeah.
So now, if f is now some function in terms of two variables, x and y, then here is the exact definition for a partial derivative. I'm not sure if so far I've just focused on telling you how to compute these things and giving you intuition. Here's the actual full-fledged, there's the definition. So the partial derivative of f with respect to x is, notice that we look at how high the function is at x plus some small delta x, y, and then minus f at xy, that height. So here's your rise, but notice that we're looking at a rise where we keep y constant. In other words, we're taking a small step in the x direction and seeing how much that changes your height.
So it kind of like the y would go out in that equation?
Not the y goes out, the y is just constant. You're not changing your y. So if you think about me being, here's my x direction, here's my y direction, here's my z direction, and there's some surface in this room, then my partial derivative here of f of x with respect to x, or f of xy with respect to x, is telling me how much my slope is if I just take a small step in the x direction. I don't change my y coordinate. My y coordinate stays the same. I just change my x coordinate a little bit. And so this gives me the slope when I change my x coordinate a little bit. Similarly, this gives me the slope when I change my y coordinate a little bit.
Is there
So you use them interchangeably.
is there a concept of like a regular derivative for a multivariable function?
Taking a full derivative of it? Yes, which we did last time. I started last time with you calculating the full derivative with respect to x and the full derivative with respect to y.
And it just gives
And you just use the chain rule to apply it to all the variables.
and it's just like implicit differentiation.
Kind of. Okay, so quick recap on partial derivatives. There's a full definition, keeping that intuition in your head for what those things mean. Okay, now we have our wave equation right here. This was, remember, giving us that particle's displacement from its equilibrium position as it shifts back and forth and knocks its neighbor, knocks its neighbor, knocks its neighbor. Typically, not typically, a lot of the time when we are talking about sound waves, we don't want to think about it as a wave in the particle shifting back and forth. Instead, we want to think about it as a wave in terms of changes in pressure. High pressure areas, low pressure areas. High pressure areas, low pressure areas. And that pressure wave as what's carrying the energy forward.
Right.
That's right.
Good? And I tried to give you intuition for how that would work with the picture last time, a little drawing, with how you send longitudinal waves and then you could see the cluster of a bunch together and a bunch spread apart. A bunch together and a bunch spread apart. That's the pressure way of thinking about it, rather than think about how that actual one molecule is jiggling back and forth. And so, that is what we first are going to do. So here's our wave equation, perfectly good wave equation, but it's in giving us the displacement from equilibrium. We want one now that gives us the displacement pressure from the equilibrium pressure. So a pressure equation that tells me this much higher than atmospheric pressure or this much lower than atmospheric pressure.
Which is the sound you're saying.
That's how we want to think about sound waves. We want to think about them as pressure waves rather than thinking about them as shifting back and forth. Well, we want to be able to go both ways. It helps to be able to rationalize these waves in both contexts.
Right.
So now we're going to derive a wave equation that is going to be in terms of the pressure. So I want to get my pressure in terms of x and t. With me so far what we're after?
X and T.
In terms of some position and some time, this equation should tell me what the pressure is going to be at that exact instant. Because as I'm talking to you, what's happening? We're getting this little bit of space right here is shifting between high pressure, low pressure, sending a pressure wave forward towards you. And so at some specific position, at some specific instant of time, it's going to have some specific pressure. And so that's what we want this equation to be, is one that gives me the pressure at any position at any time. And we're going to keep things simple for ourselves and keep it still thinking about these pressure waves going one-dimensionally. Good so far? Now, since we're going to be sending these pressure waves through these fluids, these mediums, we need to go back to our bulk modulus. Our bulk modulus related changes in volumes to changes in pressure.
Is that a P on top?
So, yeah, sorry. This is delta P for change in pressure, delta V for change in volume. The V here is your initial volume. And then this B, this constant that relates them, is some constant depending upon the material. So water had a certain bulk modulus.
Okay.
This is a way that you can rewrite the equation that I think makes more sense. Makes it easier to reason about. For some fluid or whatever I have, if I make the volume smaller, what happens to the pressure?
Increases.
The pressure increases. So that's what this is saying. Notice that the pressure, the change of pressure is negative, the change in volume. If the change in volume is negative, the change in pressure is positive.
Mm-hmm.
If the change of pressure is positive, if the change of volume is positive, then the change of pressure is negative. If I increase the volume, pressure goes down. If I decrease the volume, pressure goes up. And then how much it goes up depends upon both how much you change the volume and
Awesome.
on whatever the material is that you're compressing.
What? And that V on the bottom is your initial one?
Yeah, the V on the bottom is your initial volume, and then delta V, it's a ratio of your volumes. So taking this room with the air that it is right now, if I decrease it to half its size, that would be the same as taking, I don't want to say a balloon because a balloon's inflated, but the increase in pressure in decreasing this room to half its size would be the same as for some larger room, decrease it to half its size.
That ratio is the same?
That ratio is now going to be the same. That's what you care about.
Right.
You don't really care about the actual just change in volume. If I take a balloon and I only change its volume, small balloon, and I only change its volume by a few cubic centimeters, that increases the pressure much, much more than decreasing the volume of this room by several cubic meters.
Yeah.
So it's not the change in volume that matters, it's what portion, what ratio of the volume you changed it by. That make sense?
Yeah.
So giving you back intuition for that, we'll be using these equations to relate our pressure to our volumes. That's what they give us. So I know I'm going to be coming up with some equation for pressure, and I know that I can relate a change in pressure to a change in volume. Good so far? Okay, so let's set up our physical scenario. So here we got some cylinder right here with some cross-sectional area A. I should have used a different letter because this A is not the same as this A for our repeat equation.
Yeah.
No
So-
amplitude.
That A is our cross-sectional area of this cylinder here, which is full of some fluid. With me so far?
Yep.
And this right here at this end is going to be a piston that we can push forward. Good?
Yeah.
Now, because I can't draw 3D very well, this picture down here is the exact same picture that we have up here, just a completely sideways view.
Okay.
So looking at completely side on. So the area over here is the area there. You see what my picture's saying?
Yep.
Yeah.
Okay. And now what we're going to do is we're going to take this pressure, or we're taking this cylinder, and we're going to apply a sound wave to it. We're going to send a sound wave to it. So this is the very instant when we barely start our sound wave, so it hasn't affected anything in the fluid yet. And then we're going to go forward in time a little bit and see how things have changed. Good so far?
Yeah.
Okay. Let me think, did I say all that right? Y1 xt. Oh, no, I did say that right. Okay. Okay, so now, down here, we have now sent forward some sound wave, some pressure wave through this type of material. So, now Y1, right here, is just going to be our displacement function that we have up here, this same wave equation, at position xt. So we've gone forward in time from here to here, some amount of time t, allowing this wave to travel into this medium. So that's what the t is. And y2 is just looking at that exact same wave, but at some position x plus delta x.
Right.
So remember, since these are longitudinal waves, x plus delta x is this molecule's equilibrium position, but it's currently shifted this much forward because there's a wave there. This one is this molecule's equilibrium position, but it's currently shifted to y1. And there's no reason those have to be positive. They could have been negative, shifted back some, forward some, because they're shifting back and forward around their equilibrium position. So here are the two equilibrium positions. Good so far?
Mm-hmm.
Okay. Now, what was our initial volume?
A, or
It was A times your length.
So our initial volume for this portion that we care about, going from y1 to y2, wherever those would have been initially, is going to be from right here to right here.
A times x plus delta x.
Well, what is this distance right here?
That's y2 minus.
We're on our x coordinate here, so x is however far we are from 0, which could be clear over here. So we're looking at this little chunk right here. What is the volume of this chunk?
Isn't that
X
y2
plus
minus
dx.
y1?
No, because y2 is clear out here, y1 is clear out here. Our initial one, before the wave was in there,
Yeah.
delta x would have been at the
Oh.
same position right here.
Right.
What would our initial volume have been? For that portion right there.
X plus dx.
What is this width?
That's
This is x plus dx. What's this width?
dx.
It's just delta x. It's our change in x position from one point to the next point.
So it's a dx.
Why should we care?
Huh?
What's the x for then?
And that's just how far we are on our x coordinate system. Our x coordinate system can have its origin clear over right here. Here's x plus delta x. What's that width?
If x is 0.
Look, if this were 5 and this were 5 plus delta x, what would that width be?
Delta x.
Just delta x. It doesn't matter what the x is. Here's x.
I thought x was 0.
Oh, I did something. X. Here's x. Here's x plus delta x.
Yeah.
That width is just delta x. Good?
Good.
So before the wave was present, the initial volume was just a times delta x.
Okay.
Good?
Yep.
Now the wave is present, so things are shifting now. And so the air that was occupying this space is now occupying this space. Those same air molecules, because they're all shifting back and forth however they're shifting. So we get some change in volume, maybe positive, maybe negative, but there's some change in volume here. So here's our initial volume, which is just a times delta x. Our new volume is going to be our end position. What is this coordinate now?
Delta x plus y2.
Maybe zoom in on this a little bit. Okay,
It's x plus delta x plus y2.
this coordinate, what'd you say?
X plus delta x plus y2.
Perfect. So x plus delta x gets me to here, plus y2 gets me to here. But now, our new width is from this dotted line to this dotted line.
So
Yeah.
x plus y2.
So we need to subtract off the y1. We overcounted our distance too far.
Right.
That doesn't make
And
sense.
y1 and y2. are
Sorry,
opposite.
forget your x. I just realized you said it wrong. I just thought you said it right. This distance right here is delta x, from here to here. This distance is now y2, from here to here. So the distance from here to here is delta x plus y2.
No x.
No, the x is just getting us to this point right here. We already had this conversation.
Okay.
This shouldn't change if x were 0. Imagine x were 0. It doesn't change anything.
Yeah, so, okay.
Okay. So this distance, delta x, the distance from here to here, y2, the distance from here to here is y1.
Yeah.
And y1.
So what is this distance?
Yeah, delta x plus y2.
Delta x plus y2, now minus off the y1 portion.
And y2 and y1 are not the same distance here, right?
No, they are completely random. y2 could have actually been back this way, son.
But that's the
It's just how far the particle that was here has shifted from its equilibrium position. And it's very exaggerated in my drawing just to make things clear.
Oh, that wouldn't be the same. Okay.
Like really, when I'm talking to you, the amount that those molecules, air molecules are shifting back and forth is teeny, teeny, tiny.
Yeah.
Okay. So, our new volume, so all the air was initially in this white square.
Yeah.
That same air, some point time t in the future, now occupies from this dotted red line to this dotted red line. That's our new volume. So our initial volume was just a times delta x. Our new volume is a times delta x plus y2, now minus y1. You follow that now?
Yeah.
Okay, and so what was our change in volume? It's just this minus this. That just gets rid of the A delta X term. Good so far? Okay, there's our change in volume. Remember that Bernoulli's equation, not Bernoulli's equation, the bulk modulus equation relates volumes to pressures. So that's why we're going for a volume right now.
Right.
Okay. So now, here's my delta V. Notice that up there, when we have it related, it's delta V over some initial velocity is equal to the bulk modulus.
That's the initial volume, isn't it?
Yeah, V naught is the initial volume. So, going from here, follow that red line, going up to right here. All we're doing now is dividing by V naught. So take this equation and divide both sides by our initial volume.
Okay.
Good so far?
What does that get you?
Huh?
What does that get you?
Well, you'll see what it gets us. Now remember that y2 minus y1, those are actual, those are these.
Yeah.
So plug in those. And now, what does this look an awful lot like?
Like a derivative.
Like a partial derivative. Notice that the t is staying constant, and we're taking a small step in the delta x direction.
So that's your derivative with respect to that's your partial derivative of x.
Your partial derivative with respect to x is what this is going to be in the limit.
Right.
So now taking the limit of this, your delta v becomes a dv, and that's, so dv over v is just going to be the limit as delta v goes to 0 of delta v over v, which is now just going to be the limit as delta x goes to 0 of this thing. So just take what we had, this equal to this, and now we're going to take the limit as delta x goes to 0.
Why did your v naught turn into a v?
Just keep it more general. When we were using the v up here, it was the initial velocity, or
Why?
initial volume. So just relating it to our equation that we have up here.
Okay.
Okay, so your small change of volume with respect to, or over v, is then just going to be equal to this limit. This limit now, like you said, is going to be exactly what we mean by the partial derivative of y with respect to x. So dv over v, right there. Partial derivative of y with respect to x, right there.
So your change of volume over v is the partial derivative of y
With respect to x.
with x.
Yes,
And
that's
that-
what we showed so far.
And that's the same as our original wave equation.
Yes, and this y is exactly what we were talking about from this wave equation right here. And so we already know how to calculate the partial derivative of this with respect to x. We did that last week.
Yeah.
But you can just do it again. If you do the partial derivative with respect to x, what do? You treat t as a constant.
Yeah.
So the derivative of cosine is
Negative sign.
negative sign, so that's going to become a negative sign, and then using your chain rule, you're going to have to pull out a k.
Right.
So it's going to be
Negative.
negative sine, pull out your k. I put AW for amplitude of the wave so we didn't confuse it with the cross-sectional area. That's the only reason for that subscript there.
Yep.
Good so far?
Yep.
Good.
Now, looking at Bernoulli's, why do I keep calling it Bernoulli's equation? This bulk modulus equation up here,
Because it's a e.
taking the limit of both sides of this, you would just get dv, you'd get b times dv over v is equal to negative dp. Or rewriting it backwards, negative dp is equal to b times dv over v.
As the limit as delta v goes to 0.
Yes. As your change in volume goes to 0, your change in pressure goes to 0. So, those follow each other. So that's how we get this equation, and now we already know what dv over v is.
Yeah.
That's this.
Right.
So substitute that in, and now you just have that extra b constant.
Wow, that's a big derivation for something simple.
And now notice that you have a negative on both sides,
Yep.
and so those can go out. And so there you go. That gives you your pressure wave equation. Now, you might be a little confused. Wait, we had a dp here,
Yeah.
and now we're using a p here.
Right.
What is dp?
Your change in pressure.
Your small change of pressure. And that's what we mean by these wave equations. How much the pressure has changed from equilibrium. So you need to keep in mind, this equation does not give you the pressure at any point. It gives you the change of pressure from equilibrium at any point. The same way that this equation did not give you your y coordinate at any point. It gave you your displacement from equilibrium at any point.
Okay.
So that makes sense why dP is exactly what we were after. And now, what does this equation, what does it tell you the max your pressure can ever be?
KBA.
Just KBA, because the biggest assigned function can ever be is 1. So max pressure is just K times your bulk modulus times A, where A there is not the area, but it's the A from our other wave equation, the amplitude of your other wave equation.
K is your wave number.
K is your wave number. So notice what this is saying is that max pressure, what increases it? First off, actually jiggling the particles back and forth more, making them jiggle further, is going to increase your pressure difference. That makes sense. It's going to crunch them up more and separate them more when it's on the other end. Your bulk modulus, that makes sense. It's resistance to being pushed around anyways.
That has to be bigger.
Yeah.
Oh.
Right. If I get a shift in a stiffer material,
That's big pressure.
it's going to have a bigger pressure difference. Getting my water molecules to jiggle as much as my air molecules are jiggling
It's way big pressure.
is a way bigger pressure.
And K is your.
And then K now is your wave number, which is going to be related to your frequency.
Yeah.
What was A?
This A is the amplitude of how much the molecules are actually shifting back and forth.
I thought that's what B was.
No, B
Oh,
is
how hard
a
it is.
property of the material. B is a constant for the material. That's the same B as right here. So B is big. For water, it's small for our atmosphere. And B is bigger inside of inside of a really compressed air and less in smaller compressed air.
So it would change in between where you were in the atmosphere.
Yes. But just not very noticeable unless there were big changes. Good?
Yep.
Okay. Now, something important to notice is how your pressure and position are related to each other. Anytime I have two graphs like this, I always try to use blue to represent pressure and red to represent your displacement and position.
Okay.
So trying to tie the intuition together, notice that these are kind of phase shifted from each other by a quarter of a wave. Now they don't really have the same amplitude. I should have made my blue go to some different height.
They're gonna have different amplitudes.
Yeah, they're most likely going to. Unless B and K happen to multiply together to be exactly 1, they're going to have different amplitudes. Okay, but outside that, they'll just be phase shifted off of each other because the argument to their trig function is identical. And so trying to draw this out pictorially, so let's say we have a bunch of air atoms right here, air molecules, and now I'm just going to try and plot exactly what this position function is saying. Try and give you some intuition for this. So over here, at 0, we have red is high, which means our air molecule is displaced in the positive position a lot. So this air molecule, according to this wave, is currently right here. So here's what our air molecules looked like before there was a wave. Now I'm drawing them exactly as they look at this snapshot in time where this is their wave. So this air molecule has a big displacement in the positive direction, so it's located right here. This air molecule, it has a pretty big displacement in the positive direction, so it's now located right here. This air molecule has no displacement in the positive direction. So it was right here, it's still currently right there. This air molecule has displacement in the negative direction, so rather than being right here, it's back right here. This air molecule has a big displacement in the negative direction, so rather than being right here, it's right here. This air molecule has a displacement in the negative direction, so rather than being right here, it's right here. This air molecule has no displacement in the x direction, so rather than being right here, it's right here, no displacement. And then I think you can finish putting the picture together yourself. And so notice what's happening is right here, we're getting high pressure. Over here, we're getting low pressure. High pressure, low pressure, high pressure. So the blue, I'm trying to graph now the pressure. So here's your high pressure points. Here's your low pressure points.
Why are they offset then?
I'm trying to give you intuition for why they're offset.
Oh.
Notice that where this molecule wasn't moving is where pressure was at its lowest. No displacement, lowest pressure. Similarly over here, no displacement, highest pressure.
Okay.
Trying to give you intuition for the relationship between the displacement wave and the pressure wave.
So basically the tops will be where the red line crosses? The axis?
The top,
He's saying the highest pressure is where it crosses.
Like the highest pressure and the lowest pressure?
your highest pressure is, where it crosses the x-axis. Yes, where your air molecules aren't moving
Yeah.
is going to be your high points and your low points in terms of pressure.
Hmm.
It's going to be where they're all crunched up together and one can't move, or where they're so rarefied it doesn't have a preference one way or the other, and so it's not moving.
Okay.
And so they're just a phase shift of each other. That is great intuition to have. And that's why they're just a phase shift of each other. And of course the mass says they're just a phase shift of each other, because one was a cosine function and now one's a sine function. So the cosine function starts out at its max, goes down, sine function starts out at 0.
I thought the cosine and sine were phase shifted by half a wave.
Phase shifted by half a wave.
He said those were phase shifted by a quarter.
They're phase shifted by a quarter of a wave. Oh, the reason you're thinking that is pi halves.
Oh.
Pi halves is a quarter of your circle. That's probably where the halves is coming from.
I see. Yeah.
So yeah, cosine and sine are just phase shifted by pi halves from each other. Good? Try and get that intuition there. Why it's coming out the way that it is, I don't know. Anything else before we move on to some examples? So this is going to be one of those sections where I feel like the derivations are way more to follow than how hard the examples are. So now let's just do an example.
So the derivations are harder than the examples or easier?
I think examples are going to be relatively
These examples
easy.
in the book.
There are going to be a lot of plug and check. Yes. So now do an example 1 from your book. We're talking about some sound wave in the atmosphere, and it's given that the maximum pressure difference for some dude screaming is 3.0 times 10 to the minus 2 pascals.
Really small.
So it's, as this wave is going, that he's screaming out, it gets this much higher than atmospheric pressure and this much lower than atmospheric pressure.
Okay.
That makes sense?
Yes.
So that's how much it's shifting. Our job now was to find the max here now. How much are those particles actually shifting back and forth? And you'll see how absolutely teeny this is. Even just jump ahead to the answer really quick. 1.2 times 10 to the minus 8 meters. So it's hardly any shifting back and forth. It's very teeny.
Wow.
But so that's going to be our job, is to find that. He's screaming with a perfect frequency of 1,000 hertz. And we know that the speed of sound that we're going to use is 344 meters per second. And then the book also had to give us that the bulk modulus for the atmosphere at atmospheric pressures and at 40 degrees Celsius, I think it always says, or 20 degrees Celsius, I mean, is 1.42 times 10 to the 5 pascals. Maybe put just a pause and say something about temperature. You're going to notice over and over again the example problems or the homework problems say at this temperature, at this temperature, at this temperature. And it's because our atmosphere, air, changes a lot with temperature. It's not like water. Water, you make it 30 degrees colder, 30 degrees warmer. It doesn't expand much, it doesn't contract much. It kind of just sits there.
Right.
Take a balloon, blow it up, go stick it in a freezer. It get much smaller. Now keep heating it up, it's going to keep expanding till it pops. So that's why it's always giving you the bulk modulus for air at some set temperature. I think it's always going to be 20 degrees Celsius or something like that. And when you look it up on your table, that's why it gives a temperature there. Good? Now how do we calculate our A max? Well, just from this equation right here, we're just going to solve for the A. So A is just going to be P max divided by K over B.
Why does that give you the max amplitude?
Amplitude is our max. We do P max here to specify that it's the biggest this is ever going to get. A is the amplitude, and so A max is just A.
Okay.
Good?
Yeah.
Okay. So, A max is just going to be P max divided by B times K. We already have this information given to us and B given to us. Our only job now is to figure out K, our wave number. Two equations you remember for K, it's either lambda over 2 pi or it's omega over velocity. Those are the two that you're going to want to have in your back pocket for the wave number. So you can look at that equation from last time or have one that you have memorized. K is omega over V. Remember what omega is by definition. 2 pi frequency. And V is a given number to us. So now we have 2 pi. The frequency is given to us as 1000. V is given to us as 344. So plug 2 times pi times 1000 divided by 344 into your calculator, and it comes out 18.3.
Radians.
Yes. Because of the pi. It's going to be radians per meter.
Weird.
And that's just because the most basic definition of K is going to be 2 pi radians divided by wavelength, which will be in meters. Anyways, units don't particularly matter, but there, now we have what K is. So now we have K, we have B, we have P max. So for P max, you plug in 3 times 10 to the negative 2. For B, you plug in 1.42 times 10 to the 5. And then for K, plug in 18.3. And then that will come out to 1.2 times 10 to the minus 8 meters. Good?
Yep.
So a lot of these are going to be more plug and chug.
We're doing Doppler effect too.
Hopefully.
How many pages do you have total, by the way?
I don't know. We'll find out.
Okay.
But remember, we
Are
can.
you doing this just to keep them for next year? Or-
No, I'm doing this. Oh, you weren't in discrete math. My back's right. Can't stand right now.
You can't stand.
No, it hurts.
Do you have a wheelchair?
Yeah, this chair has wheels on it. Okay. I can hobble my way through. I just don't want to stand for an hour. That'll wreck me. Okay. Next one, interesting example. So inside of your ears, you've got some bone. Pressure waves vibrates that bone. Here's exactly what the bone looks like.
It's a bone? I thought it was memory.
It's a sequence of bones. So there's a sequence of 3 bones. You can read the example problem to find out exactly what they're called.
Incus, Malleus, Staples.
But so out here, we have the atmosphere. In here, we have your inner ear fluid, separated by this cone-shaped sequence of bones. Obviously, that's not what they look like, except for in color. Okay, so our sound wave is going to be pushing on this bone, which is then going to be pushing on this fluid, vibrating back and forth.
Okay.
Good so far?
Is that a solid cone?
I'm representing it as a solid cone. It's really a sequence of bones.
So that the pressure's, the wave's not like going,
It's just jiggling the sequence of bones back and forth.
so it's not like passing through it.
No, it's jiggling it. So, jiggling the bone.
Probably like waves.
Now, the bone has
Airs.
a surface area here of 43 times 10 to the minus 3 square meters,
Okay.
which is very small. And then at this end, 3.2 times 10 to the minus 3 square meters. Good?
3.2?
3.2 times 10 to the minus 3, yeah.
Alright.
Maybe zoom in a little bit. And we know what's part of what's given to us is a velocity that the wave that results in the fluid travels is 1,500 meters per second. And we know the velocity it travels through air is 344 meters per second.
What are we solving for?
So our job is to find a couple things. First off is to find the max pressure wave, P max, inside this fluid in here.
Okay.
And then the other thing we were supposed to find is how much the water shifts back and forth. I think were the two things.
Pressure, amplitude, the displacement amplitude.
So the pressure amplitude and then the displacement amplitude are the two things we're looking for. Right?
Yeah.
Okay. So, first off, notice that since this bone is jiggling back and forth, it's going to have some net force pushing on it. And whatever the net force is pushing out this way is going to be the net force pushing out that way. Right? Now, we're going to think about the sound wave causing this force as a pressure wave. That's the easier way to think about it. So how does a pressure produce a force?
Pressure is force per area, isn't it?
Pressure is force per unit area. So if I want to get force, I take a pressure and I multiply it by a area. So that's exactly right. So F max, this max force that we push this bone with, is going to be equal to the max pressure from the air. So I notice I do a subscript A when I'm talking about air and F for fluid.
Yeah.
So F max here is going to be the max pressure wave of the air times S1, the area of that bone right there exposed to the air. Good? And that has to also be equal to our max pressure that we produce over here times its area. Because the pressure in here times its area has to be equal to the pressure in here times its area, because it's the same force.
Okay.
So the force that we're pushing on the bone with here has to be equal to the force that the bone is pushing onto this fluid here. And so here's what that force is from the atmosphere. Here's what that force is from the fluid, and those have to be equal to each other. Good? And so, we get that. Now I'm confused by what that was solving for.
The pressure amplitude.
Yeah. I'm guessing that's what it was supposed to be. I'm not sure why I did a capital A. Anyways, using those equations, since they're equal to each other, let's just scribble our solution over here. I know that P max A, no, not A, for the fluid. P max for the fluid is equal to
P max to the
S1 over S2 times P max of A. Because this equation has to be equal to this equation.
What did we get? How did we
So
get?
P max of this times S2 has to be equal to P max of this times S1.
How
Divide both sides by S2.
How did we get P max of A again?
So P max of A, that's what I was just going to ask you. Is that something that gave us in the problem? Oh, that's why I scribbled that down there. Yes, okay. So the reason I scribbled this portion down here is because I forgot to say this is given to us in the problem as well.
And that's the max that's the max weight amplitude or pressure amplitude?
No, this is the max pressure in the
Air.
air. And I did a capital A for some reason that I don't know why.
That's air.
Oh, that makes sense.
Yeah, sorry.
Oh, okay.
Sorry. Very confusing when I do stupid things. Okay, so now I think it all makes sense.
Okay, that makes sense.
Okay, and I wondered why I skipped all that math. I didn't. I just wrote that math now over here for part A. Okay, so our max pressure then is S1 over S2 times our max pressure in the air. Our max pressure in the fluid is equal to S1 over S2 times our max pressure in the air. Now, since we know what our max pressure was in the air, we can find our max pressure in the fluid, which is 0.4 pascals.
We have our S1 and S2.
How hard is that pushing just a reference?
I don't know how to give a intuition for what that would be.
Is this really small? Or
Oh yes, these 1 pascal is already an extremely small number. What's atmospheric pressure in terms of pascals?
I forgot.
Yeah, it's on the order of magnitude of 10 to the 5 though,
Whoa.
whatever it is.
1,000?
So just ridiculously small.
And then pressure, so that's 0.4 pascals higher than atmospheric pressure.
Or lower.
Or
It's
lower.
the max displacement from atmospheric pressure that the thing gets.
So your ears have the same.
But no, so this is how much from whatever the
Ear.
equilibrium pressure of the inner ear fluid is.
Okay.
So this is how much your inner ear fluid's pressure is shifting from equilibrium. This one was how much the atmosphere, or how much your sound waves pressure was shifting from atmospheric pressure, which is just almost nothing. Ridiculously small.
Wait, what unit is that in? Is that in pascals as well?
Yes, that's also in Pascal, sorry.
Okay. And it wants us to find the amplitude of the movement.
Yes, so now we figured out how much the pressure is varying. Now the question is, how much are those water molecules actually jiggling back and forth? Now, in the previous problem, we did air molecules jiggling back and forth, and we found that they were moving back and forth on a scale of 10 to the minus 8 meters.
So we expect it to be smaller.
So we expect it to be much smaller if it's a water molecule.
Is it actually water?
It's mostly water.
Okay.
So all sound is just movement pressures.
Yes,
That's insane.
that's exactly what it is. Changes in pressures or displacement in jiggles. Jiggling creates pressure displacements, pressure changes. Okay, so the bulk modulus for our fluid, for this water, is given to us as 2.18 times 10 to the 9. Ridiculously massive. Our omega is
2,000?
2,000 times pi because the frequency was 1,000 hertz.
No, it was it was. Did you write it down?
Is that what it was here?
Yes.
Does it say using example 1
Using.
or something to that effect?
Oh.
Example 2.
No.
Where did that omega equals 2,000 pi come from? Must have said something.
Oh, yeah. Never mind. You are. Just
Oh,
not-
it said using the same sound wave from example 1.
For the sound in example 16.1.
Yeah, I hate when they do that, but they do that a lot.
It was just so hidden, but yeah.
Yeah, sorry, when I first started these notes, I was not intending to do class this way. This was just me going through it.
That's interesting.
So, that's where omega equals to 2,000 pi comes from. And then, so our wave number for our fluid, what's our wave number? Is just omega over velocity. The velocity was given to us.
As speed of sound?
No, inside the fluid. So it's like the speed of sound in a fluid.
Oh.
Sound travels much faster in water than it travels in the atmosphere. And it travels through the ground much faster than it travels through the atmosphere. So one of the things you might have seen in like movies is someone out in the wilderness, they're being tracked as though they put their ear up to the ground to try and hear if people are coming or whatever.
Does that work or is that myth?
I have no idea. I would guess that there's something to it since they do it.
It would work if you had to make a sound.
True, like the region effect.
Never tried it. Okay, so our wave number in the fluid is just omega times the velocity, or divided by the velocity in our fluid, which those are now just numbers that we can plug in. So 2,000 pi divided by our velocity was given to us over here. And that's going to come out to 4.2. And now we know how to calculate our max amplitude inside of our fluid. It's just our max pressure divided by the bulk modulus times our wave number. And now those are all numbers that we have. Our max pressure we already calculated right there. Our bulk modulus, that was just given to us in the problem, the bulk modulus for water, that's right here. And then our wave number is what we just solved for right here. And so multiplying that all out, and you're going to get 4.4 times 10 to the minus 11 meters. That's how much those water molecules are jiggling back and forth.
How does a jiggle work? Because there has to be a force to pull it back and pull
It collides into the forward thing, and so it bounces back.
It collides into each other, is what you're saying?
Yeah, it's the same way you think about you holding a bouncy ball. You chuck it against the wall and it bounces back to you.
Yeah,
What
but
if
it's-
instead there were another bouncy ball perfectly in the air?
It would.
And then you go and you can bounce against that ball. Well, in that case, it just fall to the ground. But
On a table or whatever.
if you throw it into a bunch of bouncy balls, and then you whack it, it'll come back to you. Billard ball. Okay, you break in billiards. You open with your hit. It bounces back to you and starts jiggling them forward. And they can jiggle other ones forward, another one forward, another one forward. Now imagine you kept hitting the, what's it called? The white ball.
The cue ball.
The cue ball, thank you. Imagine you kept hitting the cue ball over and over again every time it came to you. And you can start just jiggling on this endless billiard ball table of all these jiggles going out, going out, going out, going out. That's what's happening. As you're talking, you keep whacking the air molecules right next to your vocal cords, which collides, carrying out the collisions further and further and further.
Yeah.
So that's all it is. Okay, so that's how you create the jiggling, back and forth. Lots of jiggles. Okay, so there's a cool little example problem that has to do with our hearing. Next, let's move on to calculating the speed of sound. You might remember when we calculated the speed of a transversal wave, we came up with this equation, where the F, remember what the F was? Force. Force of what though? If I've got a string and I'm setting a wave down a string, what increases the velocity? What did you say?
Tension.
Tension.
Oh.
So the force here is the force of tension for that string, that rope, whatever it is. And then the mu was
Your
Density of the rope.
your density.
sorry, I'm in discrete math mode. I thought that was the expected value.
Not expected value this time. Density. And in general, we said it's going to be your restoring force divided by the thing that's resisting motion will give you your velocity.
If you were, as an example, to drag your nails across the chalkboard, how are you moving sound waves? Like,
So-
how does that work?
The chalkboard, as I'm dragging it along, is jiggling.
The chalkboard jiggling.
Think about like dragging a bristle along something. It catches and then drifts. It catches, moves, catches, moves, catches, moves.
On the grooves, you say?
Yeah.
Just one bristle, like on a toothbrush or whatever. Catches and then shifts, catches, shifts, catches, shifts, when you drag it enough. And so it's not some continuous perfect flow. It's catch, 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 catch. Jiggle, 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 jiggle. It's not a perfectly smooth surface. If you drag your finger along pretty much anything, you can kind of feel it slip and then move, slip, move, slip, move.
So if it was a perfectly flat, frictionless surface, it wouldn't make any noise.
Then it wouldn't make any noise. But the fact that you're able to catch things on it is going to create some of that jiggling. As a catch, let go, catch, let go, catch, let go.
That's why it's effective to do with your nails. No,
Oh.
your fingers.
Yeah, drag your finger across a chalkboard, you're not going to get anything.
Is that how stereos work then? So they just
The way a stereo works is, you notice that you can feel your stereo.
Yeah.
So what's it doing? Here's one way to think about it, is it's literally just
Moving near.
moving something back and forth like this. That's all it's doing.
A bunch of electromagnets that just move the disc back and forth.
electromagnets.
Magnets.
Yeah, so you send a current. So an electromagnet, basically sending a current makes the magnet stronger. Getting rid of the current gets rid of the magnet. So you can have some magnet set up here,
It's so weird.
and then some electromagnet that you send a current through. And then turning this on and off, so making it stronger, weaker, shifts this back, forth, back, forth, back, forth.
Interesting. That makes sense.
And so you have some electrical signal, which is telling you how to do it. And that electrical signal goes through, setting it, making it stronger, weaker, causing this to actually jiggle at whatever frequency you want, producing a sound wave.
But even for so complicated sounds, how did they get all those complicated sounds?
All the complicated sounds, exact same way. Remember what we did with superposition.
Yeah.
You can always represent a combination of waves as a single wave, superimposed on a bunch of different waves. So if I've got this wave, and I've got this wave, and I've got this wave, whatever, combine all those together, and that's going to have some resultant wave. And I send this wave through, and it's going to produce a sound that would have been produced by having this, this, and this all together.
That's cool.
That's how they do it.
Beatboxing.
Yeah.
Anyways, so speed of sound now. So speed of sound, when we were talking about transversal wave on a rope, then it came out this way. V equal to the square root of F over mu. where F we thought about as our restoring force and mu was like our resistance to move. Now, we're going to be sending it through some sort of medium, like the atmosphere. Notice that our resistance to move is exactly what our bulk modulus gives us. It's how hard it is to get those things shifting around.
So it's a mu?
No, so it's going to act like our restoring force. The higher the bulk modulus, the more the material is
Not moving.
trying to restore itself back to how you shifted it from equilibrium. So this is it trying to force itself, you can think about this as trying to force itself back to equilibrium, and then the actual density of the material is going to affect how hard it is to, how much it resists it being shifted. So
So it's
density will still be it resisting the shift. Our bulk modulus is like our restoring force trying to get it back to the way it was, right? Tension was trying to restore your rope back to just straight. Your bulk modulus here is the material trying to restore itself back to no pressure. The higher the bulk modulus, the harder it is to have a pressure change. Good? And so we would expect our equation for velocity to now look something like this, which it will. So now we'll go over the derivation, but that's just trying to prime your intuition.
Is that a row or a p?
That's a row. I will always try to do my p's with straight lines, and my rows I'll always try to round on the top
Okay.
to try and help tell the difference. But yeah, not the best handwriting. Okay, now I'm going to have to talk about momentum, and I don't want to use p. So I'm going to use L to represent momentum. It's another letter that's frequently used for momentum.
Didn't we use?
L for angular momentum, yes.
Yes.
So we're using L for just momentum. So L is going to be mass times velocity to help us avoid using a P.
We need more letters.
Yeah. Remember, we had the same conversation last time, so maybe I don't need to stress it too much this time. But change in momentum with respect to time gives you force. Your net force acting on the thing.
Yeah.
So if you integrate your net force with respect to time, it gives you a change in momentum. Good? Okay, so now let's talk about our picture and what's going to go on here. So I got some tube here. Again, this is a cylinder tube, and we're just drawing a two-dimensional version of it. Here I've got some piston in the tube. Initially, the piston is just there. It has some force pushing it this way and some force pushing it this way. The force is being dictated by the pressure inside the tube and the pressure over on this side. Good? So we're starting out some equilibrium position. If I were to take just a tube right here in the middle of our classroom, stick a piston in the middle, that piston's not going to move. Why? Because the pressure on this side is the same as the pressure on this side. Good so far? That's our equilibrium position. Now, what I am going to do is on this side of the piston, I'm going to increase the pressure by some amount delta P, some change in pressure.
Okay.
What is that going to do? It's going to cause our piston to shift forward some. So here it is shifted forward some. We're going to assume that this picture is time t seconds after this picture. So I applied some change of pressure for some amount of time t. Now, since the piston moves forward, it's going to compress all the air over here. Good?
Yeah.
Okay. So one of two things is going to be happening. We're going to be pushing the actual piston forward, and so this piston is now going to be moving forward with some velocity v sub y. And that is going to be how much those molecules are actually being pushed forward.
How fast are you going?
The air molecules. Notice that as a piston moves from here to here, we're actually pushing those air molecules forward. So v sub y times t is how much the air itself, those actual molecules sending the wave, are being pushed forward. On the other hand, we have the velocity now of our pressure wave traveling out, which is going to be faster than the air molecules are actually traveling. Does it make sense why the pressure wave travels faster than the actual air molecules? I'm pushing those air molecules, but they jiggle and jiggle and jiggle, sending a wave forward faster than the actual air molecules are being pushed forward. So those are two different values. V sub y is how much the piston is actually pushed forward. V here is going to be how fast that pressure wave is traveling, the velocity of our actual wave.
Which
You're
is
saying the individual compared to the whole.
Right, so when I'm sitting here talking to you, I create small pressure differences. The speed that the sound wave travels to your ear is very different from the speed of the actual atoms that I pushed forward to get the jiggling started. Those are two completely different velocities. And the actual air molecules right here don't have to reach you in order for you to hear me.
Bounces.
It's just the jiggling effect is all that matters.
Yeah, that makes sense.
And are those two related?
They're related because one causes the other.
Okay, that's what I thought.
So creating a change of pressure here, which is bunching up these air molecules, creating a pressure wave going forward. So here's how far the pressure wave has moved.
Okay.
Over here, beyond that dotted line, pressure hasn't changed at all yet. So this is someone who hasn't even heard the sound yet. The sound wave has only reached to here, the piston has only reached to there.
we're trying to find the velocity of the sound wave.
We are looking for this V, the velocity of the sound wave. That's what we care about.
That's for in general for any fluid.
In general, for any fluid. Any medium that the sound wave is traveling through.
Cool.
Good so far?
Yep.
Okay. Now, really quick, let's first calculate the mass of the system. What is the mass of the air that I have right here moving forward?
It's your density times your volume.
It's your density times your volume. Perfect. What is my volume of this portion?
It's your area times your distance.
Your surface area times your distance, and what is the distance that we care about?
For which part again?
B.
So notice when we talk about rho, the density, that is going to be the density of the air when there was no compression.
Yeah.
So what volume should we use to calculate the mass of air in this portion? We don't want to use this volume. We want to use the volume that air had before we started compression.
So V times T.
So it's going to be Vt for our length times A for our volume times rho for our mass. So that's what we're doing here. Mass is going to be volume times rho, but not this volume, the volume before we started the compression. Because now that we compress it, rho changed here. We don't know what that rho is.
Right.
We just knew the rho before we started compression.
I see.
Okay, so volume is going to be area times velocity times t. I tried to remember to do this, but I also forget to do it. Since it's hard to tell the difference between volume and velocity, I'll try to remember to curve the start of my velocity v's
That helps a lot.
to make the difference. Okay, so mass is volume times rho, which is area times velocity times time times rho, where this is the velocity we care about, the velocity of the sound wave. Good so far?
Yeah.
Okay, and now what is our momentum then? Our momentum is going to be mass times the velocity that the air molecules are actually moving at, which is the v sub y.
Yeah.
Not this v. So two different velocities here. So volume times how fast the air is actually moving forward
In the what?
in that y direction. Yeah. And that will give us now the momentum of the system. What was the momentum up here? 0. Nothing was moving. The momentum here is just this. And so our change in momentum is just going to be this momentum. Those are going to be one and the same thing. Because our initial momentum was 0.
Right.
So I know that net force times my change in pressure is equal to, or let me say that better. We just barely found the momentum, right?
Yes.
We haven't used this fact yet. So I'm about to use this fact.
Okay.
So what is my net force on that piston?
Oh, it's
Change momentum.
No, remember P here is pressure. We're going to use L for momentum.
Oh.
But just thinking about it over here.
Yeah.
What is the net force on that piston? It's being pushed this way with a force of pressure times PA,
So it's
pressure
not
times
like-
area. And it's being pushed this way with pressure plus our change of pressure times area. And so the net force on the piston is just going to be our change of pressure times area.
Oh.
That's the net force. When our change of pressure is 0, there is no net force on the piston, and it's just at equilibrium.
Yeah.
So it's our change of pressure times area that gives us our net force on the piston. Good so far?
Yeah.
Okay. So what does that give us? So looking over here, multiply both sides by time. What do I get? My change of pressure times area times time is equal to my change in momentum. When you integrate a force with respect to time, you get your change in momentum. My force times my time gives me my change in momentum, which is just the total momentum of the system, because our initial momentum was 0.
We have to integrate it though?
Okay, let's integrate this really quick. Integrate that with respect to t, what do you get?
At T.
Net force times t. Net force times t. So let's make sure that's very clear. We did integrate. That's where our t came from. Good?
Oh, okay.
And that gives us our change in momentum. So I'm just rewriting this equation right here in terms of hours now.
You can cancel out the T and the A there. right?
Exactly. So cancel out the t and the A and the t. That gets us right here. Follow that so far?
UI. Row.
Okay. Again, remember, it's the velocity is what we care about here.
Yeah.
Okay. Now, reminder of our bulk modulus equation. You can see that obviously that's going to come up somehow, some way. So use our bulk modulus. What does that tell us? That tells me that a negative change of pressure is equal to our bulk modulus times our change of volume ratio.
Yep.
We know our change of volume. What's our change of volume? That's when we go from this one down to this one. So we lost this portion of our volume.
Yep.
What is this portion of our volume?
VYT.
VYT gives us a base times the
Times
area.
Yeah.
So, our change of volume is VYT, sorry, I wrote that really small, was not consistent. VYT times our area, negative because our volume got smaller. So our change of volume is negative. What was our initial volume? That's a V. V times T times area was our initial volume.
Would that be at the bottom? Shouldn't that be a?
Initial volume, VT times A. Change in volume, negative VYT times A.
I'm saying for your, where it says B times that, didn't you write the wrong B for your volume? Shouldn't that be like a spiky V? Because you did velocity as the curve V, isn't it?
This is velocity times time is my base,
Okay, that's.
times area gives me my volume.
Oh, that's super, okay.
Velocity, so this is the velocity of the sound wave, this is the velocity that the air is moving at.
Got it.
So this is our change in volume, this is our initial volume. Look at the picture one more time just to see that that makes sense. Our initial volume was this right here, which has a base of V times T. This base is just V times T, times the area gives us our initial volume. What was our change in volume? That's the volume we lost over here. And that has a base of V sub Y times T, and then times the area gives you it. And negative because we lost volume. So that's this equation. So we substituted in our change of volume right there, and our initial volume right there. Good so far? Okay, notice T's go out top and bottom, A goes out top and bottom. And so negative change of pressure gave me negative Vy over V times the bulk modulus. Get rid of the negatives, and it simplifies to this. Because all the T's and A's went out, and we got rid of the negative on both sides.
Just solve for B again.
Solve for V.
Yeah, we're looking for a V, aren't we?
So now, yeah, so now notice we have our change of pressure is equal to this, and our change of pressure is equal to this. Two equations with two unknowns.
So you substitute.
Plug them into each other. So I'm just going to set them equal to each other. That's equal to this. That's what we did here. Now I need to get all my V's on the same side, so move the V over. Oh, also notice V sub y goes out on both sides. So move the V over and the rho down.
V squared is equal to V. Rho.
V squared is equal to our bulk modulus over rho, which gives me V is equal to the square root of our bulk modulus over rho. And there it is. There's our derivation for our velocity, which is what we would have guessed pretty much it would have been. Good?
Mm-hmm.
So they both rely on constants. I guess that makes sense. Okay.
This one relies on a constant for the fluid. This one relied upon the tension, which is not a constant.
Right.
The velocity that sound goes through a rope, not sound, a transversal wave goes through a rope, very much depends upon the tension. The wave speed goes through this room. There isn't a way to really put this room under tension. I mean, I guess that would be like increasing the pressure or something like that, which would then change the bulk modulus.
Right. If you wanted to, could you look at how the speed of your sound wave changes as you change the bulk modulus as a function of time?
Yes. And we will get to situations where we'll have a bit to say about when the bulk modulus is affected by temperature in particular. That's a big one that affects it.
Okay.
So we'll have a little bit to say about that, but not much until next week.
Ratio.
Or the week after that. Next week is test week, right?
Do we have tests this week?
Yes,
I'm going to check my syllabus.
we for sure do. Test after all the wave stuff, and then test after all the thermodynamic stuff. So 100% you have a test next week.
So double test.
No
next week?
question about it.
Yeah, double test.
Wait, do we have a test?
Double
next week?
test for discrete math.
Yeah.
Yeah,
Well,
that
is
will be
double
easy.
test, so that's two.
You can just show up to the screen math.
Okay.
He's right.
Now, that was sending it through some solid medium, or some three-dimensional medium. This was our equation.
Uh-huh.
What about like sending sound down like a metal rod? So it turns out it has the exact same equation, but you just replace it with Young's modulus rather than the bulk modulus.
Oh.
It comes out the exact same.
That's the one, is that like the compression tension one?
Yes, and like a steel beam, for example.
Makes sense.
Or sending now a sound wave down a string, right? You get two cups hooked up with a string. That is not using transversal waves to send the sound. It's using longitudinal waves to send the sound. Different wave. And so calculating the velocity now of that would be calculated this way.
How long can you have a cup and a string in a cup before you can't?
Before it dissipates, I don't know.
That's all.
Wait, you still have
Yeah, it's probably going to
strings
depend
and
upon a lot of
cups,
stuff. Go try it.
You ever tried that?
What?
It's like you were never even a kid.
Holy cow. What did you even do?
Pokemon cards.
Okay. So it comes out the exact same way. Now, as we were already talking a little bit, the bulk modulus for gases very much depends upon the actual pressure. And then our gamma here is going to be some constant for the material. So whatever your pressure is very much affects the bulk modulus of that gas. And your pressure is very much dependent upon your temperature.
Do we use a T for temperature?
Yeah, capital T for temperature. So this capital T is representing temperature. That's a gamma representing a constant. That one is called your ratio of heat capacities. You'll know more about that when we get to thermodynamics. I'm not going to go too far into this, so we're not doing any derivations, just to show you it. So for what we call an ideal gas, for those of you who have done chemistry, you'll know what that means. And we'll find out what an ideal gas means next week. Then the velocity can be calculated as, again, some constant depending upon the gas in question. In this case, we're using a gamma to represent that. Another constant, R. For those of you who have done chemistry, that's the same R that you see from your ideal gas equation over here, where you have pressure times volume is equal to nRT. It's that exact same R. Or it's the R you derive when you use this version of it, where you take Boltzmann's constant and divide it by Avogadro's number, and that's where you get that R. For chemistry, guys, coming from those equations. Anyways, R is just number 8.314. You'll get very comfortable with this in our next 4 chapters. And M here is your It's referred to as your molar mass. It's the amount of kilograms per mole you have. Sorry.
No,
Are you not familiar with what a mole is?
I don't know.
It's like
It's
1
the
to a
number.
billion or something.
It's just a giant number.
It's the number of atoms in like a
6.2
big of gas.
times 10 to
You can say it's how many hydrogen atoms you need to get 1 kilogram of hydrogen.
It's a lot of atoms.
You know, you need 1 mole of them. Okay, so
You're really good at telling me.
that's a mole. So the M here is your molar mass, which is kilograms per mole, which you can kind of think about as being very much like your density. In some sense, how heavy the gas is that you're talking about.
What is
This
molar
equation and this equation are the exact same things when you make all your correct substitutions.
mass? Oh, it's density for gas. Okay.
Yeah, essentially.
Molar mass is density for gas.
Standard temperature and pressure.
Kind of. It's mass per mole. So we'll have a lot more to say about this as we go. In order to use this equation, last thing you have to know is that your temperature T needs to be in terms of Kelvin. We haven't talked about absolute zero yet. Again, we'll talk about that in thermodynamics. But
Kelvin's the way to go.
Kill.
Kelvin, 0 degrees Celsius, Kelvin starts out at negative 273.15 degrees Celsius.
Which is just
And then they increment the exact same way.
Yeah, it's
Increasing the temperature by 1 Kelvin is identical to increasing the temperature by 1 degree Celsius. It's just what they call zero is different.
so they just shift it.
Yeah, it's the Kelvin scale is just a shift of the Celsius scale. Celsius calls zero where water freezes. Kelvin calls zero what we
Or
refer to as
absolute.
absolute zero.
Yeah.
So Kelvin is nice.
Kelvin is a very natural choice for temperature, and it's one we'll use the most in thermodynamics.
yeah, it's really cool
Round of
because
applause.
your conversions quite nicely.
So anyways, when you take into all those considerations, here's exactly how you calculate it. The bulk modulus here that you use is for air at atmospheric pressure at 20 degrees Celsius or whatever it is. So it would be the same thing you get if you plug that into this equation. So identical equation, you might have one problem where you have to use that. So far that's just something to memorize and know exists, not something to derive yet. You'll get much more comfortable with all that come thermodynamics. Okay, next example, we got some sonar system, some fish or something. It is sending out sonar waves to detect an object. Roughly, how does sonar work?
It's like a radar
Noise.
sound.
Sound.
So the sound wave goes forward and then it bounces back. And you can,
Right, and you listen for the echo.
Yeah.
And depending on how long that echo takes to get to you, tells you how far away that object is.
So this is an echolocation fish.
Yeah, so an echolocation fish, I think it's supposed to be a dolphin or something. Might have even been a boat, I don't know.
Whale did that.
Something. Something in the water using sonar to detect something.
So submarine.
Could
Or
be.
something, yeah.
Alright, so it sends out its little sonar waves, and those are going to come back and bounce off. It sends out its sonar waves at a frequency of 262 hertz. Our job is to find how fast this wave is traveling, and to find its wavelength. We know the bulk modulus of water, so that's given to us. And we know the density of water, that's a rho. The density of water is 1,000 kilograms per cubic meter.
It's really nice.
So velocity we can calculate as a bulk modulus divided by the density, which comes out to 1,480 meters per second. That's how fast this sound wave is traveling through the water. Notice it does not depend upon the frequency.
What?
So sound waves travel
They
through
don't
water
move,
at the same
right?
speed, just like air. The speed of sound in our atmosphere does not depend upon the frequency.
Can the animal even process the sound wave coming back that fast?
Can what?
Like the animal has to, it's using echolocation, it has to know the time between it sent the signal and the time that it gets back. Can it process the information fast enough to actually tell how far it is?
You can catch that. Did you have to process exactly what the velocity was, what the trajectory? You evolved to have just an instinct on how to do these things. You don't need to know any physics to catch it. You don't need to do any sort of calculations.
Right.
You just know how to respond.
No.
But like at a certain point, if the object is close enough to the animal or the fish,
you have a sense for how far away this is, based off of those photons bouncing off, going back into your eye.
Yeah, but I'm not sending this.
You even kind of have sonar to an extent too. Like when I put you into a really crowded room and you talk, you can kind of feel that it's crowded and it's full of stuff. Or when you're in an empty room, you can kind of tell just by the sound waves coming back to you. So you have an instinct for this. It's not a massive processing problem.
Right.
You're evolved to do it, and so you just know.
Yeah.
So hard for us to get a sense for it. It'd be like trying to explain sight to a blind person.
But
Well, this one we can kind of get some intuition for because we kind of have it.
but if the speed in the fluid was fast enough, then at a certain point the wave would return back to the animal before the brain could shoot out another signal. You know what I mean?
Think about the speed of light.
But I'm not shooting photons out and then measuring how fast it gets to get back to me.
That's true, but those photons are bouncing off of me, going into your eye, and you're instantly updating your understanding of what my position must be.
I gotta think about it.
They don't think like a computer. It's just some sort of instinct response. They're not trying to think about like you do, like, okay, that took me that long, let me think.
I know, but like at a certain point it'll be going faster than their instincts could process.
I don't think that.
Really?
No. The same way that I don't think light is going so fast that our instincts can't process it. Or
Yeah,
flick
but
of an
we're
object or
not having
whatever.
to time the light in our brain.
No, but trying to figure out. Imagine I gave you the problem of, I give you some pictures, try and locate exactly where this object is. Just 2 pictures. Where exactly is the object relative to those where the camera was taking those 2 pictures? That's an insanely complex problem.
Yeah.
Like when we do tracking of an object, have robots do it through the air, we have to do all sorts of shenanigans to try and keep track of it, or do it in very controlled places where we have tons of sensors to help figure out where that object is and where it's going. That is an extremely difficult problem.
But super easy.
But I throw it to you and you didn't process anything, you just kind of looked at it and you had a feeling, you knew, and you caught it. And it's amazing.
But what if you threw the object so fast that I didn't register that it was there before hitting? You know what I mean? Like my
Then I do
instincts-
that.
My instincts.
And so that would be that you registered the rock was there while you were swimming so fast that you didn't register it was there by the time you collided with it.
Well, I guess my point is like, if the speed of the sound was fast enough, then it would be imperceptible whether it bounced back to you and it was.
Oh, it's not going to be some little pulse. Sound travels fast.
Right.
It doesn't change. I mean, it does change how you hear it, but you're still going to hear it. If I increase the sound wave that I send to you tenfold, you'd still hear it.
I'm just saying, if the speed of the sound was fast enough, then it would return back to the fish at such a rate that the fish wouldn't be able to instinctually understand. It would be basically imperceptible. Like, imagine you have a rock 100 feet away and a 500 feet away.
Right. There needs to be some way to get the difference between these different things. So yes, if the speed of sound were to be close to the speed of light, then this would just be almost impossible.
So it's
Can't
just,
distinguish the difference.
that's
but-
really fast. Like, that's
When
very
we're talking
fast
about
speed.
these types of speeds, I don't think so.
Weird.
Just an instinct, not so much a processing.
Right.
Okay. Another one with the speed of sound. Speed of sound in air at 20 degrees Celsius, so that's one that they're going to use over and over again. Okay, so giving you one example using that equation. So they said, find the speed of sound in air at 20 degrees Celsius using this equation. Now, this is mostly just a bunch of looking up.
That's chemistry.
1.4, that's a constant.
That was our chemistry equation, right?
Yeah, this is the chemistry equation. 20 degrees Celsius, convert that to Kelvin. Add 273.15 to it, in other words. So here's our T. Our molar mass for air, once again, that's a constant that you just look up. Those 3 things together, plug them all in. R is always the number, 8 point whatever it was. So mostly it's just plugging in constants. And the only real variable in this would have been the T, the temperature, which is what gave you.
That's just all one constant.
This is a constant for the air. This was calculated from 20 degrees Celsius. This was a constant for the air.
And M is
And
also,
R is just a constant period.
and M is constant
M is constant for the air.
for the air.
Yeah, our atmosphere has this molar mass. If our air were made out of heavier materials, that would go up. If our atmosphere were completely hydrogen, then this would go down.
Is that per cubic meter?
It's kilograms per mole.
Okay.
What's the definition of fluid?
Something that flows. I told you, it's a terrible definition when we came across it. You can almost think about what's a fluid. It's the things that follow our fluid equations. That's a fluid.
So not like a wall.
Not a wall. A wall is not a fluid.
Yeah, those cases.
Yeah, there could be cases where it's fluid. Right? When you start thinking about a giant asteroid smashing into the Earth, it might be appropriate now to treat the Earth's crust as a fluid.
That is so cool.
But relative to you and me, it's not even close.
Earthquake could do that.
Earthquake, yeah, it could play with the boundary, but there's going to come a point, is the point.
Yeah.
So, depends on how extreme you get. Anyway, so you calculate all that, and we get, ta-da, 344 meters per second. Which is exactly what you would get for the speed of sound if you calculate it the other way. Now they wanted to calculate the wavelength for a frequency at 20 hertz and at 20,000 hertz. Remember that these are the range of human hearing. The lowest frequency sounds we can hear and the highest frequency sounds we can hear. So the lowest frequency sounds we can hear, how do we calculate this? I didn't write the equation that we use, or if I did, I didn't.
For the wavelength?
It's not
Have
chapter
it.
16.
But what we're going to be using over and over again is the fact that velocity of a wave is equal to wavelength times frequency.
Right.
So you've definitely seen that equation a bunch of times, but that's one that we use over and over again. This is how long a cycle is. This is how many cycles per second you have.
Right.
So if your cycle is 1 meter and you're doing 100 cycles per second, your speed is 100 meters per second. That make sense? I'll take that for a Anyways, so now just using this equation. So take the speed of sound, which we know is 344 meters per second, divide it by the first frequency, and that gives you our first wavelength. So if it's a low frequency, then we have a high wavelength, 17 meters. If it's a high frequency, then we have a low wavelength,
Yeah, it makes
1.7 centimeters. Good?
sense. Yeah.
Okay. Now, sound intensity. We already talked about intensity last time, so once again, what is intensity? It's the amount of power you have per unit of area.
Oh, that's right.
So intensity is typically calculated as power over area. What was power? Two ways you can think about it. You can think about it as work over time. It's the most natural way to think about it, but another useful way that we've now used a few times is also force times velocity. Because work, you can think about as force times displacement, and displacement over time is velocity.
Oh.
So same thing.
So same thing. But here's the one that we want to use.
That honestly makes sense.
So now our job is to come up with an intensity equation for our wave. So you can find the intensity of our wave at any position at any time,
Okay.
where intensity is defined as power over area.
Power over area.
Yes, power per unit of area is intensity.
Okay.
So don't confuse those two, because intuitively sometimes it's easy to muddle up power and intensity. The power of a speaker is whatever it is. The intensity of the speaker dies out the further away you get, because that same power distributes over a larger area as it spreads out. So there's the difference there.
So isn't that just like F times V over some kind of area function?
That's exactly the way I would describe it.
Cool.
So it's like F times V over some sort of area function. Now, force over area gives us
Your pressure.
your pressure. So you can also think about it as pressure times velocity will give you your intensity.
Where'd the rest of that come from?
Intensity,
No.
pressure times volume. You get so far?
Yeah.
Okay, so now we want our intensity, which is going to vary as a function of position and time. So whatever that equation is, we now know it has to be equal to our
Pressure equation.
pressure equation at that position and time times the velocity now,
Oh.
the change in y with respect to t.
That's our velocity.
Yes, the jiggling back and forth. The jiggling back and forth.
So, okay.
So remember that our y is how much we're displaced from equilibrium. So your change in your displacement with respect to time is going to be how much you're jiggling back and forth, that velocity. That's the velocity we care about when we're talking about up here. This velocity was a velocity due to the displacement that you did work with. You can think about those little molecules as doing work, and transmitting that work down to get your energy to flow. And so it's that jiggling back and forth. That displacement is the one doing the work, so that's the velocity we care about when we're talking about power. So once again, our intensity equation then must be equal to our pressure equation times our velocity equation. We already know how to calculate this. We've already done it a couple times. You go back to your wave equation, and you just do its partial derivative with respect to t. That will give you the second half. Your intensity equation, your pressure equation, we already calculated, that's this first half. Here's your pressure. Here is your velocity. Sorry, missing a parenthesis at the end.
Sine squared.
Yeah, so I just wanted to write it out completely before we simplified, so you can see where they both came from. So now, let's simplify. All of our constants, what do we have? We have a b, we have a k, we have an a, we have an omega and an a. So putting those all together is b, k, we had a twice, a squared.
Where'd your omega go?
Where'd my omega go? Not good. Someone trying to call me. Let's see if we can squeeze it in here. Don't do that. Okay. We're missing an omega. Okay. That omega's just gone from all of them.
Did you find a way to cancel it out?
I don't think it should be canceled out. I think that's just a mistake.
Oops. Did you mess up the calculation?
We'll see what happens. Okay, following along. So intensity, omega b times k times a squared times sine squared, exactly what you said. Now, what is the average of our sine squared function? We've already talked about this, although I don't think we ever computed it in calculus, because you don't know how to do that yet. But the average of sine squared is 1/2. Sine squared varies from 0 to 1. Right? Your sine function varies from -1 to 1. Sine squared varies from 0 to 1. And it turns out if you were to integrate it over one cycle and divide it by 2 pi, then it would come out to exactly 1/2.
Why do you divide it by 2 pi?
Area divided by the base gives you your average height, which is what we mean by the average value of a function. Okay. So, here's your intensity. Your average intensity is just what you get when you replace this with a 1/2. The sine squared. Good?
Okay.
In general, when we talk about the intensity of the wave, we mean its average intensity. That's what's meant.
Then is area a function of distance here? Like the area gets bigger as the distance of the wave goes further out, right?
This is not an area, this is an amplitude.
Oh, I'm sorry.
That's why I spelled out area here so that we would not get confused.
Where'd our area go?
We didn't have area in the picture at all. Oh, sorry, we did, and then we got rid of it.
Oh, that's
With
right.
pressure.
That's right. That's right.
And I'm not sure how I messed with that. Somehow I moved that little chunk. Go back together. Alright. So yeah, sorry, shouldn't have used an A twice. Probably should have used an S for area here. Anyways, so what we mean by the intensity of the wave is its average intensity. So now, here's the intensity.
Isn't that just a constant?
Notice that B times K times A is exactly P max. Right?
Yeah.
So we can replace, just rewrite the equation. So here's my equation. Oh, I picked up my omega again. That's good. So B times K times A, B times K times one of those A's, we can rewrite with a P max. I'm doing too much in one go. This is why I write the notes for myself and not for teaching. So let's write this out so that we can see it all. What do I currently have the intensity as? I currently have the intensity as 1/2 times B times K times A times omega. Did I miss anything? It's an A squared.
A squared.
Okay, and we now know that P max is equal to B times K times A, right?
Yeah.
And then the other relationship I'm going to be using is that our velocity is equal to the square root of B over rho.
Yep.
And the other relationship I'm going to be using is the fact that K is equal to omega over B. And I'm
Rho.
assuming I'm using that.
You wrote omega in your velocity instead of rho.
Thank you. Okay. So now, with all that, we can rewrite this intensity now. Let's see one of the ways I rewrote it, as P max squared over 2 times rho times velocity. So, P max squared, P max is B times K times A, so if we did P max up here, squared, then we need a B squared, a K squared, and an A squared. So let me just put the omega here for a second. In order to get that so far, I would need a B and a K down here.
Yeah.
And so far we're still good, right?
A B and a
And a K.
yes.
Let's see, I'm somehow going to get a velocity to show up in there. How did I just come up with this?
Does it in the book?
Good chance of it. Over 2. Let's see. V I can also write here as being equal to omega over K, right?
Yep.
So here we have an omega over K.
Yeah.
So that puts it in the numerator. So I've got a P max, I don't know, a P max squared times a velocity
Velocity over B.
over B,
And you're 1/2.
and the 2 down there.
If you get the square root of rho, and B. What? B is your bulk modulus, right?
Let's just go the other way and see where this comes from.
KAB is
Let's start with P max squared all over 2 times rho times velocity. Because apparently this should be that same thing. Let's see if it comes out the same way. So what is this equal to? This is equal to B squared times K squared times A squared for P max squared, right?
Yeah.
All over 2 times rho. Don't really have anything to substitute rho out with.
You don't end up substituting it out.
Well, I'm trying to reverse engineer it to get it back to this.
Oh,
The only thing I can relate rho with is my velocity. So rho, looking up here, if I put rho over here and velocity down on the other side,
you can do that. You can just-
well, let's just write it out so I don't have to confuse you. Square root of b over square root of rho, right?
Yeah.
Then move rho over here
Oh, okay.
and the v down here, and I can say rho is equal to b over v squared.
Okay.
That one makes sense?
Yeah.
So, replace my rho with the b over v squared in the denominator times v.
One of your V's cancels out.
So one of my v's cancels out and the bottom of the bomb goes up to the top.
Yeah.
So this is equal to b squared times k squared times a squared times v all over 2b.
You need to draw.
That's literally what I have right there. Isn't
No,
it?
one of your B's.
C max squared V over 2B.
I think we're good so far, right?
Yeah.
So now a b cancels out top and bottom, and v can be rewritten as omega over k. So this is equal to, we have a b times k squared times a squared times v can be rewritten as omega over k, so then we get 2k in the bottom. Finally, the k's go out, and we get back to where we started.
Okay.
Okay, so they're equal to each other. Just have to, and I'm missing something obvious, because I wouldn't have just written it that quick unless I just saw something.
You have a lot of experience doing derivations.
Huh?
You have a lot of experience doing derivations. Because
Yeah,
I could not do that on the fly, obviously.
that, I'm missing something obvious. There's something obvious there to make those connect quickly.
2 times square root of rho B.
But there's our derivation, so you can see it comes out the same. Since I don't want to make a mess of something, I won't bother showing how that one comes out the same, but it will.
Okay.
Oh, this one, okay, from here to here you can actually see much quicker. And that one you replace this velocity with the square root of b over the square root of rho. So I get the square root of b up here, and then a square root of rho downstairs cancels out with the square root of rho in this, leaving a square root of rho upstairs.
But why is the B in the square root?
Okay, let's just do that because now that one's real easy. So starting with where we left off, with this one,
Yeah.
I'm going to replace my b with the square root of b over square root of rho just to be super clear. So we got p max squared all over 2 times rho. I'm going to write rho funny just to be super clear. P2 times rho times velocity. Velocity is square root of b over square root of rho.
Yeah.
One of those square roots cancels out with one of those square roots. So 2 square root of rho square root of b.
Hey, no, because. Okay, okay.
Okay, so that's how you get those ones. So, yeah, the jump from that to that is pretty obvious, and I'm missing something obvious on the jump from that to that, but there's something. And maybe the book explains it better. Okay, now let's talk about what we call sound intensity level, the way we measure the sound intensity level, and we do that with decibels. You've likely all heard of decibels. So we use a beta to talk about our decibels, and our decibels is in some sense a measure of how intense some sound is. Here's the exact equation that we use. 10 times the logarithm of whatever intensity you're talking about divided by some baseline intensity. Now this baseline intensity, I sub 0, is going to be 10 to the minus 12. What is this? This is the least intense sound a human being can still hear at 1,000 degree or 1,000 at a frequency of 1,000 hertz. We just had to pick some frequency in the human range, and then we had to say, emitting a sound at that frequency, what is the smallest intensity we can possibly use and still have it detectable to a human being?
Why 1,000 hertz?
We just had to pick some base frequency to use to emit the sound.
Doesn't matter.
It does matter because it turns out we're better at hearing sounds at some frequencies than we are at other frequencies.
Oh.
So we had to pick some baseline frequency, but in the aggregate, it should all be coming close to this number. So what that means is if I were to put you in some perfectly quiet room and then play a sound of 1000 frequency sound at this intensity, then you should barely be able to hear it. The very fringe of human hearing.
At what distance away?
This intensity takes into account your distance. Power doesn't. Intensity does. So whatever power the speaker would be, we'd have to calculate how far away you need to be now to get exactly that intensity at your ear.
But if it has that intensity at your ear, then it counts for the distance away.
Yes.
Yes.
Because it has
So with that, this makes it so that by definition, 0 decibels is the minimum sound a human being can hear. So if I plug in I naught into this equation, what's I naught divided by I naught?
Zero.
I naught divided, what's a number divided by itself?
1.
1. What's the log of 1? Remember when we have log, it's always log base 10. So 10 to what power equals 1? What's the exponent I have to put there? Remember, logarithms gives you exponents.
0.
0. 10 to the 0 is equal to 1. So log base 10 of 1 is 0. 10 times 0 is?
0. 0.
10 times 0 is 0. So 0 decibels is, you can barely hear it. That's what 0 decibels is meant to mean. Now let's say that I now take that speaker and I crank it up so it's 100 times louder. Well, maybe we'll start with 10 times louder. Let's start with 10 times louder. So I take that speaker, crank it up so now it's 10 times louder. What do I mean 10 times louder?
More intense.
That's a bad way to say it. So it's 10 times more intense. Whatever the power output is to that thing, I now up it tenfold. So now the intensity that you are experiencing is now 10 times greater than it was before. All right? So things are getting wild. So now this I is 10 I naught. So the question is, we're looking at 10 times log, and now we're plugging in a 10 times more intense sound.
Wait, quick question. Why do we have that 10 times in front of the
Get a
log?
stand for just a second. So at I naught, when I gave you that intensity, the decibels you heard were 0. Okay, so now I'm going to give you one 10 times bigger. So now we're doing 10 I naught. And now,
Yeah.
I naught over I naught, 10 I naught over I naught is just 10. 10 to what power gives you 10? 1 times 10 is 10, so 10 decibels. So if I turn it 10 times louder, 10 times more power, that's from now on, every time I say louder, I mean that much more power. Okay, so if I increase the power output, the intensity by 10, then you now hear 10 decibels.
Or put you.
So if you increase it by 1 decibel, you double it.
Well, now let's increase it by 100 and see what that gives us. So, 100 I naught over I naught is 100. 10 to what power gives you 100? 2 times 10 is 20. So if I now go 100 times the initial one, that's now 20 decibels. What if I give it 1,000 times more power?
3.
Then that's going to be 1,000. Log base 10 of 1,000 is 3. 3 times 10 is 30. So if this were 1,000, I naught, that would be 30 decibels.
Why is the 10 in, why do we have the 10 in front of the log? What's the 10 times the log for?
The 10 times the log, to make it count up this way, this is just
Oh.
how you want a tenfold increase in intensity to count. And we want it to count every 10 decibels. So notice that as we increase this side exponentially, we're increasing this side linearly. So this is what we mean by a linear scale.
Doesn't that mean that if you increase the decibel by 1, you double the intensity?
If you increase the decibel by 1, you double the intensity?
So 10,
No.
10 to 11. What's the
There
difference
is.
in intensity between 10 decibels and 11 decibels?
Between 10 and 11? whatever the coefficient we need to be to increase it that way. The way that we have it set up, so for some logarithmic scale, a logarithm looks something like this. We have it set up so that every tenfold increase here corresponds to every increase by 10 here corresponds to a tenfold increase here. That's the only simple relationship you're going to be able to say. You're not going to be able to say what increasing 1 decibel is easily.
Okay.
And how that shows up over here. Because, well, yeah, I'm just not going to be able to say it.
And how does that?
You can calculate it if you want, but
How does that sound to our ears?
how does that sound to our ears? So they created a table in the book somewhere to give you some sounds, some relative sounds for each of these things.
Military jet aircraft is 100.
What page are you on?
521.
521. Is this on an angle now?
No.
No, it's just messing with my eyes. All right, 521. So here's a table to give you a sense for different decibel sounds.
Threshold of pain. What the heck is that?
Where's
It
the-
starts to hurt your ears.
Huh?
This is where it's so loud it hurts. It physically hurts you to
Yeah, but
listen to.
that's so relative.
No.
Yeah.
It's going to be roughly the same for all people.
Where does your eardrums? Where do they rupture?
I have no idea.
No, I think
What's a riveter?
like
Huh?
basketball game for each other.
What's a riveter? The one right below the threshold of pain.
I'm actually not sure.
These are terrible. Like this is the worst scale I've ever seen. Like I could have done
Quiet
so
radio,
much better things. Threshold of pain.
That makes sense.
Threshold to a pain, that's one that
Do
pretty
like
much
a
makes sense.
motorcycle or something.
Ordinary conversation, yeah, should have done like a, well, they have a busy street traffic, so that's going to be about
That's a good
70
one.
decibels.
Vacuum cleaner, motorcycle.
Yeah, vacuum cleaner would have been a good one to have on there. But, so, there you go. There's a different,
Quiet automobile. What the heck is that? It's a quiet automobile.
it's not a loud one. It's one that's quieter than a conversation.
Wait, when was this book written?
Probably early 2000s. If I had to guess the number, I'd guess 2008. Oh.
2004.
Oh.
First copyright was 2004. Is that right?
You're the one looking at it.
I don't know what I'm looking for. So.
Okay. Anyways, so that's how sound intensity works. And so notice that increasing the intensity so let's just really quick do something ridiculous. Let's say we increase it by 1,000,000 now. So 1,000,000 is 10 to the 6, right?
Yeah.
So
So it's
1,000,000 times as much only would come out to 60 decibels. 1,000,000,000,000 times as much would only come out to 90 decibels. So you have to drastically increase the amount of power that goes into something to change the decibel level that you hear.
So that fighter jet would have been.
That's what I was trying to tell you guys the last time, just intuitively. I said very, very roughly, you have to increase your power tenfold to make it seem twice as loud as it was before. Very roughly.
Yeah.
Mm-hmm. I believe that.
And you have a similar thing with light. That one you have better intuition for. Right? You turn on a light bulb in a room and it lights up the room. If you turn on a second light bulb, it doesn't double the brightness as you perceive it. And very roughly speaking, you need 10 times that amount of light to feel twice as bright.
Which makes kind of sense.
So there's decibels. There's how we measure decibels. A decibel is a measure of intensity. Good?
Mm.
Measure of relative intensity. Intensity relative to some threshold level. Okay, so doing two examples. So I think example 5 again made reference to the wave in example 1. So once again we know that our max pressure for some sound wave that we're sending out is equal to 3.0 times 10 to the minus 3 Pascal. Rho, I'm guessing that's rho for our atmosphere, 1.2 kilograms per cubic meter.
Yeah.
And then speed of sound, 344 meters per second. We emit a frequency of 1000 hertz. Our job is to find the intensity. Now the intensity, we have those three different equations we can use for intensity. Since we were given rho, velocity, and the max, I'm trying to screw up on my laptop. Then obviously it makes most sense to use that equation right there.
Right.
So literally just plug in the numbers, since they were all given to you in the problem. This next one says using examples 1 and 5.
1.
Yeah, going back to example 1, they kept referencing example 1.
Ooh.
And if I find P max and A max, if the wave instead has a frequency of 20 hertz, but the same intensity as what we calculated over here. So now I got a wave that has this intensity, but now it's just has a frequency of 20. Good so far? So we're looking for P max and A max. Here's the frequency, here's the intensity. Well, P max squared is just equal to, again using that equation, 2 times P times V times the intensity. Sorry, rho times velocity times the intensity.
Mm-hmm.
Just using the equation I keep barely dragging off screen again. Can I get both? Right there. So that doesn't change with frequency. So P max is still just going to be 3 times 10 to the negative 3. That in no way depends upon frequency. Now, I also know P max is equal to K, or B, our bulk modulus, K, our wave number, and then your max amplitude. And so your max amplitude we can calculate this way. Notice that your max amplitude depends upon your wave number, which does change with frequency. So if we have the same intensity of a wave, but we lower the frequency, that is going to drastically change the amplitude that those things are moving back and forth. If it's the same intensity, it doesn't change the pressure, but it's going to change the amplitude.
Okay.
So it'll be moving back and forth more distance, but not as quickly, lower frequency.
And how about the same pressure?
And still have the same pressure. So you can get the same pressure with fast over a short distance or slow over a bigger distance is essentially what this is going to be telling us.
Makes sense.
And so now we can calculate the A max. The A max is equal to P max, we still know. B is our bulk modulus. And the wave number, I'm calculating that as omega, probably should have wrote omega over velocity first. Omega over velocity,
Yep.
where omega is 2 pi the frequency. Don't know what that was. Okay. And so now we have all those numbers. We have the frequency, we have 2 pi, we have the velocity, we have the bulk modulus. So you just plug in the numbers, and A max now comes out to this. Whereas before, it was, well, before we were talking about 1000 hertz, right? And now we switched to 20 hertz. 1000 hertz is how much bigger than 20 hertz?
500.
Try again.
50.
50. And so now this amplitude is going to be exactly 50 times bigger than it was from example 1. Oh, I wrote it here. So in example 1, here was our amplitude, how much the wave is moving back and forth. Lower the frequency, gives us a higher amplitude, and since we changed the frequency to be exactly 1/50th of what it was, we increase the amplitude by exactly 50. Good? Okay. Next one. Find I1 and I2 for beta 1 is 28 decibels. Remember, use beta for decibels. And beta 2 is 92 decibels. So I know a sound is 28 decibels. What is the intensity I must have heard? Or if I know a sound is 92 decibels, what is the intensity I must have heard? And I want to do this to remind you guys how to work with log equations, since you probably haven't had to do that since calculus. So I'm just going to show you as a side step. Let's take this equation and solve it for intensity. So if I give you the intensities, you know how to get the decibels.
Yeah.
Let's make sure you also know how to go the other way. If I give you the decibels, make sure you know how to get the intensity. So I'm going to solve this for I. You with me?
But you need E for that.
Well, you'll see exactly how we do it. So first, divide both sides by 10. And that's the hardest part. Okay. How do you undo a log?
You raise it to E, don't you?
Right, if I have y is equal to natural log of x, put both sides to e, that means e to the y is equal to x, right? And that is because what is natural log? Natural log, by definition, is log base e. So that's why you raise to the e. If instead we have log to the 10, if I know y is equal to log base 10, when we don't put it, it always means base 10 of x.
Right.
Then you do 10 to the.
Then 10 to the y is equal to x.
Yeah.
Okay, so to go from here to here, raise both sides, do 10 to whatever that side was on both sides. So do 10 to the whatever this was, and then 10 to the that. But the 10 to the log base 10 cancel each other out. I'm saying that terribly, but I think you understand what I'm saying.
Yeah.
Okay, and now just solve for I, so move the I naught over there. So I is equal to I naught times 10 to the power of beta over 10. And now with that, the problem's trivial. What's I1? Just plug in beta 1. What's I2? Just plug in beta 2.
What are your units?
Units, watts per meter squared.
Oh, power.
Watt is power. It's the amount of power per square meter you have. Remember, it's going to be real easy to think about intensity as power. And it's real easy to mix those two up. Intensity is power per unit area. Your speaker has power, you hear an intensity.
Also, how do we actually calculate the logarithm function? Like, does it have a definition?
Yeah, we went over the definition of natural log in calculus. It comes from E. What we did is we defined E.
Or for any logarithm for any base and any number, what's the formula for calculating it? You know, like
Oh, there isn't as straightforward a way as there are for other things.
Really? Like for sine, it's just infinite sum, isn't it?
Oh, for something like that, yeah, you can express your functions as these infinite Taylor series expansions. And for pretty much all nicely behaved functions, they can be approximated as arbitrarily well as you want by some polynomial. So that would be a Calc 2 topic,
Oh,
that you learn how to do that. Okay. So now let's talk about standing waves. So with these standing waves, I'm only going to draw the top part of the wave, not the bottom part coming and bouncing back. But standing sound waves, so I'm using red for our displacement one and blue for our pressure one. Here's our displacement wave for a sound. Here's our pressure wave for a sound. With me so far? Once again, just graphing them out. This time, I was more careful and made sure that the amplitude of these two things were not necessarily the same. The red one has amplitude A, the blue one has amplitude B times K times A, whatever that is. Good so far?
yep.
Okay, now, the way you get a standing sound wave is the wave goes out and then bounces off something and comes back,
Yeah.
interfering with itself, same way that you got standing waves before. And so this would come back on itself, back up like this, back down like this, back up like this. And so once again, you're going to get, wherever it crosses the x-axis are going to turn into your nodes, your points that never move. And then the middle points in between them are going to be your antinodes. And sorry, red wasn't a great color there. It doesn't show through as good on the screen as I would have liked. But notice, I'm using A for antinode and N for node on the various waves. A node for a pressure wave is always an antinode for the position one, for the displacement one. And an antinode for your pressure wave is always a node for your displacement one.
What's a node?
The node is one that does not change in a standing wave.
0.
If going back to when you like pluck a string on a guitar, if we were to watch that wave, I'll do one example of what it might be. So it might be something that looked like this at one instant of time. And then at the next instant of time, this one's going to move down some, that one's going to move up some, and it would look something more like this. And then another instant of time, it would look something more like this. More shallow, more shallow. Here's the actual string. And so that will come down, this will go up, and they'll swap positions, swap positions, swap positions. This part of the string looks like it's not moving. That's a node. An antinode is a part that moves the most. And then we don't have a special name for anything in between. So nodes don't move at all. Antinodes have your most movement. They move through your entire amplitude. Good?
Yeah.
Okay.
It's like local min and max, isn't it?
Almost. Your nodes will be, they'll be always on the x-axis. Your antinodes are going to be mins and maxes. So my antinode here is at a max, my other antinode here is at a min. The nodes are always on the x-axis. They don't go up, they don't go down, they always just sit there. And the rest of the wave keeps moving back and forth the way that it moves. The nodes just sit there, antinodes moving the most.
Okay.
Does that make sense? Okay, so standing sound waves, very important that we understand that relationship between the displacement wave and the pressure wave. So let's do an interesting problem to help give you intuition for these two things. We've got some speaker right here, some distance away from the wall, I don't know. This right here is a wall, and then this is just for us to help measure on. But here's an actual physical wall that we're going to send that wave towards. So the speaker emits the wave, going along, and this is a speaker that's capable of emitting just a perfect pitch, one frequency wave. All right? So this wave is exactly whatever frequency, doesn't even matter. Some frequency F. It's going to go, and it's going to hit the wall, and then it's going to bounce back on itself. I drew the blue version up there for the pressure one. Maybe stop and think about this for a second. Why is the pressure at its max when it hits the wall?
Because it's the wall.
Because it's crunchy.
It's crunching, so you got some intuition there. Another thing to think about is if your sound wave hits the wall, how much can the air molecules jiggle if they're up against a physical object?
Limited.
They can't. And so notice that wherever it hits the wall has to be a node for your displacement one. And so it has to be
A
a peak for your pressure one,
Your antidote.
your antinode.
Okay.
Yes, so it has to be an antinode for your pressure one wherever it hits the wall. So I know whatever this wave is, as it's going along, when it hits the wall, then it has to be at an antinode. And then it's going to bounce back at us. Our question is, so a speaker emits a sound wave of some length, lambda, we don't know what it is, at a wall. How far from the wall should you stand to hear no sound at all? In other words, for the wave to perfectly interfere with itself.
We can do that.
Yeah. So as this wave is going, the node parts aren't going to move. The other parts are going to keep shifting up and down, transmitting a sound. So if you were exactly right here, or right here, or right here, then you would hear no sound. If it was emitting just one perfect frequency pitch and your ear were a point mass.
I've got to try that.
But there are better or worse spots where sound cancels out with it, or the sound. The other way you can think about is where should you stand to have it amplify as much as possible. And that would be you should stand at this position or at this position. Because then it will build the most. And so there's going to be places, especially when you have like two speakers, where they complement each other the best and where they cancel out more. And so you try and find that sweet spot. Anyways, so the answer here is, you can either be, remember that that's at 1/4 the wavelength. So this is 1/4 the wavelength away from the wall, or you could have been at 3/4 a wavelength away from the wall, or at 5/4 a wavelength away from the wall, etc. And so the answer is your distance just needs to be 1/4 plus however many halves you want. So you can do 1/4 the wavelength and then add as many half wavelengths as you want, and you'll always land on a node. Ooh. So thought that was an interesting problem. Good? Okay. Next one.
Whoa, that's a lot.
Wind instruments. So wind instruments, first off, there's two types of wind instruments. There's wind instruments that are open on both ends, and then there's wind instruments that are closed on one end. And so we're going to think about the types of standing waves that can exist in either of these instruments. So we're going to think about it in simplest terms. We're going to think about just a straight pipe, and we're either going to close the end or open the end. That's it.
If you close the end, how does the sound come out?
It can come out the other way. You blow into some can or whatever. The sound goes down and bounces out. So this end is always open.
Like soup?
Yeah, maybe I didn't make that very clear. This end always open. We're going to talk about the other end either being closed or open.
Okay.
And the length of the pipe. So I could have a pipe, so that's what we'll have. This will be my pipe at some arbitrary length. Green will be for open-ended cases, and we'll use red for closed-end cases. But just a pipe, either closed at one end or open at that end. Now let's think about if a pipe is open at an end. First off, what does a pressure wave look like at the side that you're using as your instrument to start blowing or whatever to make your sound? What is the pressure always going to be at the opening?
It's a little above atmospheric pressure.
It's just basically going to be atmospheric pressure.
Yeah, a little above.
So basically no change from atmospheric pressure. Similarly, if it's open on the other end, then no atmospheric pressure. So if my pipe were this length, here's one possible wavelength I could have inside it if it's open at one end.
Okay.
Because a standing wave would have to start out at equilibrium and end at equilibrium. So if it were this wavelength, or if my pipe were this long, here's one possible wavelength that could exist in there.
Right.
If my pipe were this long and open at another end, here's another possible wavelength that can exist in there. Any length that would result in it starting at equilibrium position and ending at equilibrium position.
Oh.
So pick any green, dotted green line you want on here. Say that your pipe ended at that point. From there to there, that's showing you one possible wave that could have been produced in there. You see what I'm saying?
Yeah.
Now, if it's closed at one end, again, think about the displacement. If your wind instrument is closed at one end, your displacement can't displace anymore. It's up against a physical barrier. And where displacement is 0, then pressure is at an antinode.
Yeah.
And so your pressure one, now if it's closed at one end, could end right there. It could be closed right there. Here's one possible wave that could exist in it. Or if it ended right there, here's a possible wave that could exist in it.
Oh, so for your red one.
So the red is all the possible places for a closed instrument, and the green is all the possible places for an open instrument.
Why is the red so much higher on its coefficients?
Why is red so much what?
You increment by odd numbers for your 3 lambda, 4, 5 lambda.
Yeah, but it's counting pi fourths. This one's counting pi halves. It's pi.
Pi?
Wavelengths.
Lambda.
Lambdas. What are all the other equations?
Huh?
What are all of the other equations?
So now we'll do the similar math in both cases to what we did for standing waves on a string.
Okay.
Which is, we'll calculate the possible wavelengths for a given length L instrument. We did this for a given length L string. And then we'll calculate the possible frequencies for some given length. So, if I have some length L open-ended pipe, the possible wavelengths that can exist in that are pi halves times n.
Lambda halves?
Lambda halves times n. I'm going to say that done. Lambda halves times n. You with me right there so far?
Yes.
So all the possible wavelengths that can exist in that, just solve for this. Just solve for the lambda. So for any n, that gives you a possible wavelength that can exist in that pipe. Question, if my pipe is 1 meter long, what's the biggest wavelength I could possibly have? 2 meters.
2. Yeah.
Yeah, so if L is 1 meter, then the biggest possible wavelength we can have is 2 meters. In other words, that would be, this is the length of my pipe going from here to here, and here's the wave inside the pipe, which is only half the wave. Only half the wave fits in the pipe at a time, and so the wavelength is actually twice as big as my actual pipe.
Gosh.
So, the biggest wavelength we could possibly have is 2L, and in general, you can have any nth version of that initial wavelength. So I can also have half that, a third that, a fourth that, a fifth that, a sixth that. Some integer multiple of that, so it always ends at the same height that the first one did. Good so far? Now, what's frequency? Using this equation, frequency is just going to be velocity divided by lambda.
Yeah.
So my smallest frequency that I could possibly have is going to be v divided by lambda 1. And that's f1, and we call that sometimes the base frequency, or the baseline frequency of whatever it is we're talking about. It's the smallest possible frequency we can get that instrument to give off.
And how do we find
And it's associated with the biggest wavelength.
How do we find V in this case?
V is going to be the speed of sound for all wind instruments.
Okay.
Good question. Good so far? So here's our base frequency, the smallest frequency we could possibly get. For any lambda sub n, here's a corresponding frequency. But lambda sub n is just lambda 1 over n, make that substitution. And then v over lambda 1 is just our base frequency. So in other words, you can get your baseline frequency or any n multiple of that baseline frequency. So if I can get 20 hertz as my baseline frequency, I can also get 40 hertz, 60 hertz, 80 hertz, 100 hertz, etc.
So, oh, that's cool.
So that's what controls, for some wind instrument, the fact that it can only give off certain sounds.
Like
It's
trombone.
limited by the frequencies. Yeah, by whatever it is. Probably the simplest one to think about is just like a recorder.
Just you putting your fingers over the holes.
Now your fingers over the holes changes effectively where the opening is. Because if the first hole is open, then it's as though that's pretty much where all my sound wave is going to escape, and not much is going to continue through the rest of it. And so closing off that hole effectively makes it longer, which makes that you can play lower frequencies, a deeper sound. The highest sound is going to be all the holes open. And you take a recorder and you blow it with all the holes open, it basically sounds like a whistle. Well, that's a bit of exaggeration, but that's when it's going to have its highest pitch.
Should have brought a recorder.
Yeah, not a bad idea. Anyways, you'll notice with wind instruments, a huge part of it is just clogging and unclogging holes, changing effective length. That's what it's doing. If it's closed at one end, well, now what is a possible length we can have? So if I tell you the length L, then whatever my frequency is, it has to be an odd number of lambda force. So 2n minus 1 is just going to be an odd number for any n you plug in there. If you plug in 1, it spits out 1. If you plug in 2, it spits out 3. If you plug in 3, it spits out 5, etc. So this is just giving us some odd number of lambda force. And so, every possible one, lambda sub n, just solving now for that lambda sub n is going to be, you put the 4 over there, and then divide by the odd. 4 over there, and divide by the 2n minus 1. Good? Now, what's the biggest wavelength we could possibly have? Well, that's when n is 1. So it's going to be 4 times the length for a closed instrument. So imagine that this were the length of my instrument from here to here. Notice that only 1/4 the wave fits inside of there. So you can play that wave in that instrument, and the actual wavelength is 4 times longer than the pipe I'm actually using to create the wave. So there's our biggest wavelength that we can possibly create. Now, since lambda sub 1 is equal to 4L, I can rewrite this making that substitution. And so any nth wavelength I could possibly get is going to be our biggest wavelength divided by some odd number. And all those are going to be possible wavelengths I can get out of there. So if I can get 2 meter wavelength, I can get 2/3 meter wavelength, 2/5 meter wavelength, 2/7 meter wavelength, 2/9 meter wavelength, etc. Now, once again, just using this equation to solve for the frequency, if here's our lambda sub 1 is 4L, what's f sub 1? Well, that's going to be velocity over lambda sub 1. Oh, I didn't make that substitution right there. What's f sub 1 in general? It's just velocity over lambda sub 1. And f sub n is just going to be velocity over lambda sub n. Velocity over lambda sub n. Now let's substitute in lambda sub n, this equation. Since we're dividing by it, put the 2n minus 1 in the top and the lambda sub 1 in the bottom. Which gives us this. Velocity is still there. And now velocity over lambda sub 1, that's exactly what f sub 1 is. And so 2n minus 1 times f sub 1. So any f sub n frequency we can get is going to be some odd multiple of our baseline frequency.
What is an example of a closed-end instrument?
I think some organ pipes do that.
Organs. So how does opening a hole make it sound squeakier?
So if you open the hole,
Sooner.
so say I was blowing this wave along and I come along and I suddenly, rather than having it open there, I open it here.
Yeah.
Good?
The way, yeah.
So now if it's open here, one of the wavelengths that would have worked in this one is the one that started right here and just went up, touched, and then came back down. That big long one was one of the possible ones in here. Because it started at zero pressure, or at equilibrium pressure, and ended at equilibrium pressure. Now, since I open this hole, that wave is no longer allowed.
That's how it goes up in pitch.
So there's tons of waves inside.
Oh yeah, I just drawing one arbitrary wave. It's going to be some baseline frequency and any multiple of that frequency that pipe produces.
So why
When you blow into a pipe or an instrument, you're not just producing one frequency. You're producing a whole range of frequencies, but they're going to be, depending on what kind of instrument it is, they're going to be n multiples of f sub 1 or odd multiples of f sub 1,
So
depending on what kind of instrument it was.
you can have two people that blow into the same instrument, and they both sound the same when they do it. Why do they sound the same if there's a bunch of different frequencies being produced?
Because you're both giving the same basic frequencies to begin with. A good source of like white noise is just the wind. It has a good mixture of just all sorts of frequencies, and so the idea is you're throwing a ton of different frequencies in there. This is kind of related to resonance. Certain frequencies are going to work with it, others aren't. And when you blow on it, your mixture of frequencies is going to be pretty much the same thing as when I blow on it, my mixture of frequencies.
Just because the air comes out the same?
Yeah, just because you have very little control over, when you blow, the massive range of frequencies you're producing. And so the ones that resonate with it are the ones that are going to be reproduced in it, which is going to be some combination of these things, the ones that are stable standing waves. Right. Okay, so there's wind instruments.
This is the last page.
We're halfway.
Okay, we'll skip that last one and just talk about the last concepts. So, one of these concepts we already talked about, but talked about it a bit more explicitly, which is interference, in particular, constructive and destructive interference. So let's say that I am capable of producing just a single frequency sound. Here it is. And you are also capable of producing this exact same frequency sound. Notice what happens if you go lambda halves, whatever that wavelength is, so I'm producing the sound and it has its wavelength. If you were to go exactly half the wavelength ahead of me and start producing that exact same sound, what's going to happen?
Simple motion.
They'll cancel out.
They're going to perfectly cancel out with each other. Because the resultant is a superposition principle. Add the two waves together.
Yeah.
And so the result is that they're going to perfectly cancel out. And so you can perfectly cancel me out. Now, notice that if instead you were to stand exactly right here, or exactly lined up with me,
It would construct.
then you would get constructive interference, and it'd be as though we did double the amplitude of the initial wave.
Which makes sense.
Which makes sense. So for destructive interference, the distance you want to stand away from me is lambda halves plus some amount of wavelengths after that. So you could have stood here, or you could have also gone and stood here, and it would have produced the same effect. And to get constructive interference, you want to stand some number of wavelengths away from me.
Right.
So that's how you get constructive and destructive interference.
Stand like slightly translated to the right.
Then it just slightly messes with it. And right there, it would sound mostly like it's constructive.
How do you know if it's on a higher a note or an anti? How do you know that by the sound? Or is there any way?
If we set up this experiment and you were able to stand exactly lambda halves away from me, and we both did that, Caleb would hear nothing. And then if we lined you up and got you right next to me, Caleb would hear it as intense as he was going to hear it.
Doubly intense.
Yeah.
Double the amplitude.
Wish we had a lot. So it'd be a cool lesson to do physics.
But yes, he'd hear it much better. And so we could keep moving you around until we maximize how well you can hear it. So this is what works with your speakers. Your speakers both produce the same sound. There's positions where you can hold your speakers where they're kind of canceling each other out, and then there's positions where you can hold them where it's giving the best constructive interference for your position.
That's
And so you can play with this when you have two speakers if you want, shifting them around. You're not going to get perfect canceling out like this. But you'll notice that there's positions that you can hold it where it sounds way better, and there's positions where you hold it where it doesn't sound nearly as strong. And so people who go through the pains of doing perfect home theaters put a lot of effort into setting up their speakers just right.
Yeah. Yeah. And in cars too. Cars have a lot.
And in cars too.
So how do noise-proof rooms work?
Proof.
Noise proof, just by absorbing sound waves. Sound waves are creating jiggles in the atmosphere. I can have stuff that just absorbs the jiggles and stops the jiggling.
Foam blocks.
Foam.
It's in the same way that that door helps stop some of it. It's just absorbing it. But yeah, they get, if you get the really, really good ones, what you're going to notice is that they have foam coming out of the walls, but they also have the foam coming out of the walls in a jagged pattern like this.
Yeah.
So that your wave coming in there can get eaten up by it.
And then what? Just absorb.
Well, and it's going to start absorbing it, and your smaller ones can get absorbed bigger in, and your bigger ones can get absorbed further out. And so it makes it get a nice range of waves that it can easily absorb.
Works pretty well.
So, for your really fancy ones, but if you're just like soundproofing your basement, you're basically just putting a good amount of material in between you and them with different mediums. Typically, you want something like sheetrock, air, sheetrock is a very good combination.
Right?
Air is actually a pretty good insulator going from one material to another. Yeah, that's a good combination. You want to change materials back and forth to interrupt the transmitting of the wave.
So the brick here is not a very good insulator?
The brick here
It's
is
pretty good
a
insulator.
good insulator.
That's fair.
There's a lot going on with the brick. But if you did brick, air, brick, then that would be a really, really good insulator.
But we don't.
I mean, even windows are pretty good at insulating sounds when they're double paned.
We just do regular one layer brick though, right?
Yeah, but that's a huge variety of materials. But yeah, the sounds that are going to transmit well through sheetrock are not, well, that's not the best way to say it. But yeah, it's just forcing it to switch mediums and material, eating up your sound. Anyways, last thing we got to talk about now is the Doppler effect. Doppler effect didn't have any notes written up for this. Did he get to it yet?
Beats.
What's that?
You're missing beats.
Yeah, we're not going to do beats. You can just read it. There isn't much to really derive with it. Just trying to give you a sense for what beats are. Combination of waves. But, Doppler effect.
Doppler effect.
So, you've come across the Doppler effect probably before. What's the context that you have heard it? Yeah, some car driving by. When a car's coming at you, you hear and then when it goes past you, it's lower. And so, it's like the sound of a car going past. why does it do that? What is going on here? And so let's come up with what exactly is going on. So we're going to start out with some source. I'll use S4 source. Here's our source. Source meaning it's emitting the sound. And here are sources, and it's emitting sound waves. So here's a sound wave that it emitted 3 seconds ago. Here's a sound wave it emitted 2 seconds ago. Here's a sound wave it emitted 1 second ago. And it's currently in the process of emitting this next sound wave. Now, if I would have done this correctly, these would all be equal distances from there to there to there. So don't read too much into my bad drawing.
Equal distances.
Now, it's emitting the sound with some frequency. I'll use f sub s for the frequency of the source. Right? Here I am. I'm standing right here. I'm listening very well. If I'm not moving, then I'm just going to hear the same frequency that that source was emitted with. Nothing strange. Now, the velocity that these waves are moving towards me with is the speed of sound, which we'll use v for. It's emitting them. These all have a wavelength of just lambda. Relative to me, the velocity it's coming at with me is just v. V is equal to frequency times lambda. And so all hear the same frequency that the source is emitting. Now what makes this more interesting is what happens when I start moving towards or away from the source. We'll draw the picture of me moving towards it.
Your velocity increases.
So we'll call this the velocity of the listener rather than the velocity of the source. If I'm moving towards the source, if I'm moving towards this sound wave, and the sound wave is moving towards me with some velocity v, I'm moving at it with some velocity v sub l, what is its velocity relative to me?
It's that plus v sub l.
It's v sub l plus v.
Yeah.
So if you're screaming at me at 344 meters per second, and I'm running at you at 100 meters per second,
Wow.
then that scream is coming at me at now 444 meters per second. So if the velocity of the wave relative to me, because remember, if moving with a constant velocity, that's still inertial reference frame, laws of physics have to hold. And so now, the velocity of the wave plus the velocity of the listener is now going to be the apparent velocity that that's moving at me with. And so now that has to be equal to the frequency that I hear, frequency of the listener, times the wavelength I measure. Now, we're not using Einstein here, so me moving towards it doesn't cause any sort of length contractions. I still agree that the wavelength is wavelength. So for my reference frame, lambda is still lambda. The velocity that the wave is coming at me with is now this, and so here is the frequency I hear. And how does my frequency compare to the frequency of the source? We'll say that you're the one playing the music here, so we'll call that your frequency. How does my frequency compare with your frequency? Well, over here, you just say the speed of sound for you is just this, and that's just going to be equal to lambda times the frequency that you hear. So your frequency, f sub s, is just going to be equal to v over lambda.
Yeah.
Here's what I'm saying over here. So let's relate this to that. With me so far? So I'll just maybe replace the v really quick with lambda times f sub s. So rewriting this equation down here, that v is the same thing as lambda times f sub s plus v sub l is equal to f sub l times lambda. With me? Let's see, I'm trying to get this by itself, so divide both sides by lambda. And so I'm going to get f sub l is equal to f sub s plus v sub l over lambda. And so the frequency that I hear is going to be the frequency that you hear plus some. And so it's going to be a higher frequency if I'm moving towards you, or if you were in the car listening to your own radio, whatever, but driving towards me at the same time.
It appears higher.
Yeah.
Yeah, if the relative velocity to me is up, then I'm going to hear a higher frequency. So when the car is driving at you, it's emitting the sound, its engine's emitting sound at you at 344 meters per second. But then the car is also driving at you at 30 meters per second or whatever. And so that creates a higher relative velocity that the sound wave is coming at you with,
Which increases your frequency.
which increases the frequency.
And then conversely, if you're moving
And then, yeah, notice that if your velocity, the velocity now of our listener, were negative, then that would create a negative shift down from the source frequency, and so now it would sound lower.
So if the car,
So if the car's moving away from you now,
Mhm.
is the same thing as you moving away from the car moving away from you. That's just a matter of reference frame.
so if the car was moving at the speed of sound away from you and was emitting a sound, would you hear that sound?
No.
It would just like kind of stay there, in a way.
What would that frequency be? So, if that were the sound, then what would V sub y, V over,
Lambda,
replace that with just V. V over lambda, what does that give you?
the frequency.
Which then just doubles it. Oh, that's then moving directly towards you.
Yeah.
So moving away from you at the speed of sound. Then that sound wave, that seems weird to think about,
That is kind of.
but
weird,
it just holds still.
Now what happens, so if you move faster than the speed of sound, the sound wave would fall.
Yeah, we'll talk about shock waves here in a sec. Let's stick with Doppler effect before we move to shock waves.
We stop backwards?
Yeah, I very briefly talk about shock waves, but it works better if we talk about, let me turn that off to get to my book. Sorry, I want to make sure I'm giving you the equations that they have for these, and right, in terms of what they have. No, they did it in terms of the velocities. So let me redo this one more time. The equation we have here is perfectly valid, but that's not the way that they have it. So let's redo it the way that they have it. They want to cancel out the lambdas and keep the velocities in there. So I'm going to do my frequency in terms of your frequency, but this time I'm going to get rid of my lambdas and replace it with velocities. Okay? So solving for lambda from this equation, what do we get?
That's equal to frequency over velocity.
Velocity over frequency, right?
Oh, sorry, yeah.
Okay, so now making that substitution in over here, we're going to get V plus V sub L is equal to F sub L times V over F sub S. Multiply both sides by the reciprocal of this to cancel it out over here. So doing that, I'm going to get F sub L, writing this one first, is equal to multiplying the reciprocal of this over to this. We're going to get F sub S times V plus V sub L over V. Did you follow that?
Yeah.
Or one more way that we can write that is F sub S times 1 plus the velocity of the listener over velocity. Okay, so yeah, once again, that seems to be saying to us, oh, that makes perfect sense. Wait, this is the velocity of the listener. Maybe you can't just go back and forth talk about the velocity of the listener and the velocity of the source. We'll have to think about that for a second. But what this does say is if you are moving away at the speed of sound, then you hear a frequency of 0, which that makes perfect sense.
Because it can never reach you.
Because it will never reach you.
I guess it would.
Now, it's going to be different with if the vehicle is moving away from you at the speed of sound and emitting a sound, you will hear it. That's a different scenario because the sound travels through the medium. And so what matters is who's moving relative to the atmosphere. Because sound travels through the atmosphere.
What frequency would you hear that?
I don't know. Let's calculate it. But first, let's finish this and then we'll get to one with the moving observer. Okay, so far, just did I'm moving. Sorry, we erased me. We did I'm moving and the source was holding still. And I was moving with some velocity v sub L. Good? So there's our first one. Let me just double check that's exactly the equation he has. It's going to be up higher. F sub L is equal to F sub S times V plus V sub L. Okay, he has both those. Okay. Oh, he did both ways. Okay, so he did both the ones I gave you. And I erased the first one I gave you.
You're saying F of L equals...
So he did 16.25 and then 16.26. I just saw 16.26, so I thought he didn't do the 16.25. But the other way, you can either get your lambda in terms of S of S or your V in terms of S of S. Make the substitutions, that's how we got the two equations. Okay, so now let's look at the second scenario, which is now our source is also moving. So, reset up our picture. I'm going to have to kind of just explain the drawing because it's not going to look good. Okay, so our source was right here 3 seconds ago, was right here 2 seconds ago, was right here 1 second ago, and is currently right here. Okay, trying to draw these circles correctly. When it was right here, it emitted a sound wave. Get those closer together. There, there, there. When it was right here, it emitted the sound wave, and that was 3 seconds ago, so in that time, that sound wave has traveled out something like trying to draw a perfect circle around that, and I nailed it. Okay. Now, trying to draw a perfect circle, but now it's only had 2 seconds to travel out around this one. And so now that's going to be something like, I don't know. Now around this one, but it's only had 1 second to travel. And so now that's going to be something like, I don't know. And then here's where the source currently is. There's our source. 3 seconds ago, 2 seconds ago, 1 second ago, there it is. Here's the sound wave it emitted each of those times.
Gotcha.
I'm back here. So we'll say that the source is moving that way with the velocity of the source. Doesn't matter if it's positive or negative. We'll just assume that way for a picture. And we'll have me moving in the same direction. So here I am. I'm also moving with the velocity of the listener. And I'm now hearing these sounds as they're coming at me.
You can be stationary too, right? It doesn't matter.
I could be stationary, so that would just be plugging 0 in for this, which we can do when the math is all said and done. But so here's our scenario so far, right? And now notice, the lambda here, the wavelength, is not so trivial. Now, if I would have done this correctly, the distance from here to here would have been the same as the distance from here to here.
Is this not logically?
Would have been the same as the distance from here to wherever the source currently was.
Isn't this logically equivalent to me moving away from the source as it produces sound?
No. It matters whether or not the source is moving because air isn't being, it's not being emitted from the source at a constant speed. The speed of sound traveling through the atmosphere doesn't care that I'm moving as I emit the sound. It still goes at 344 meters per second.
So the sound in front.
It's just changing the frequencies.
Gotcha.
So the sound waves are traveling out as fast as sound waves are traveling out through the medium. And so now notice, in front, the sound waves are getting bunched together, and in back, the sound waves are being stretched out.
The frequency just changes over the wave.
So we're just changing the frequency by doing this, and the wavelength. Change frequency, change the wavelength, because the velocity stays the same. And velocity is equal to frequency times wavelength. So we're changing frequencies and wavelengths. The velocity is always 344 meters per second for the speed of sound.
So if the source was moving at the speed of sound, then it would be at the very tip of that wave, just kind of.
Yeah. So if it were moving at the speed of sound, then it would be doubling this wavelength in the back. And in the front,
It would just be.
it would always be building up this front wave
Yeah.
with more and more and more intensity as it went.
Thanks.
That's a shock wave, is that right?
Almost.
Almost.
We'll get to shock wave here in just a second. And let's just touch on shock wave before we finish our derivation, I guess. What is a shock wave? That's when you're traveling faster than the speed of sound. So here's the sound that you emitted 3 seconds ago. Here's the sound that you emitted 2 seconds ago. Here's the sound that you emitted 1 second ago. And here you are. Let's pretend that this is a jet. Let me set up some nonsense scenario that gives you the right intuition. Let's say on this jet that a girl says, "A gun!" Then you hear a gunshot. Then you hear the girl scream as she dies.
Okay.
If you were outside the jet listening to it, you would first hear the girl die, then you would hear the gunshot go off, then you would hear her scream, "A gun!" Now, obviously, the sound waves are going to get completely destroyed, but gives you an idea. You're hearing into the past with a shock wave. Here's the wave where she says a gun. Here's the gun going off. Here's her screaming as she dies.
Oh,
You hear her dying. You hear the gun go off. You hear her scream a gun.
So you're saying if you're standing in front of the jet?
Oh, yeah. Sorry. You're standing right here.
Cool. Thanks.
Good point. Now, really, it just sounds like a jumbled up mess. But it gives you intuition for what's going on with the shockwave.
Similarly to how if you travel faster than the speed of light and you looked at the Earth while traveling, you would see us and then that and then back in time basically.
It's kind of like that.
Faster than my shock wave.
And if you just poofed a light year away, then yeah, you see into the past.
Wow, that's weird.
Theoretically, you can't travel fast enough.
So that's like supersonic light.
Supersonic means faster than the speed of sound, yes. And a simpler version of where you see similar phenomena is a boat in water. It's going faster than water's ready to transmit those waves that you're creating in a surface, and so it creates that big in front of the boat. So a slow boat doesn't have it. The faster the boat goes, the more it has it. And it's creating a shock wave in the water. And
Yeah,
it's just a bunch of noise.
There's a word for it though.
Okay, but let's go back now to Doppler effect and finish our calculation for the case where we've got me moving and the source moving. And so the point is that this lambda here is no longer as trivial to calculate. So what is that lambda? And we'll call this lambda b for the back of the wave because it'd be different for the front and for the back, but similar type calculation. What is that distance?
The distance of your first wave plus however far.
Let's go back to when we weren't moving.
Yeah.
So from here to here, when we weren't moving, what was that lambda? It was lambda, but lambda, how do you calculate
It
it?
is velocity over v2.
It was the velocity divided. Remember that frequency is the inverse of period.
Yeah.
Let me think about it this way for a second. Velocity times period, where period is how long it takes to emit the next wave, the next height. Okay, so lambda is velocity times period, but now you have the velocity of the wave moving that way and your velocity moving this way. So what's the lambda for lambda sub b here?
It's
Minus.
Maybe I'll just v plus the velocity of the source times t. There's the distance that the wave goes due to the fact that the wave's just going, and then there's also the fact that the source moved that way some, making it a longer wavelength for the same amount of time until we emit the next one, which is obviously just divided by the frequency of the source.
So as the speed goes up, your frequency goes down.
For a fixed wavelength,
The wavelength, yeah.
if you want a fixed wavelength.
Right.
But really, what's happening in this scenario is your frequency is staying the same. You know, you're playing your songs or whatever, and so your frequency is staying fixed, and so you're increasing your velocity, which is increasing your wavelength. The wavelength behind you.
Right.
It's shortening the wavelength up here. If we were doing this one, if we did lambda in the front, then that would have just been equal to v minus v sub s over s sub s.
Okay, so now if we're traveling at the speed of sound, that would be double the speed of sound over your frequency. Is your wavelength?
So let's see, if you're traveling at exactly the speed of sound,
That's for the front wave.
then your front wave has no wavelength. Your back wave has double the wavelength, which both those make perfect sense.
And what would the observer hear behind the source?
Behind the source, the observer hears a much lower frequency, twice as low frequency. In front of them, they hear, I don't know.
They wouldn't hear anything.
Now, you'd hear something, it's building up something right there. And just some pressure wave hit you, and it's probably just noise, I don't know. I mean, obviously, it can't just perfectly keep building. We live in a real world, but
Yeah.
the same way that when you listen to this, you don't hear the girl died and the gunshot, then, he has a gun. Instead, you hear just a bunch of noise all muddled together, however it starts interfering with itself. But there's a simplified version of it. Okay, so now what we want is your frequency relative to their frequency, right? That's what we're after here. So what's the frequency of the listener hears?
Oh, yeah.
So frequency of the listener is going to be equal to, what is the velocity that I observe it coming at me with?
It's the speed of sound minus the velocity of the source.
Well, what was it before last
How are you
time?
moving forward?
So it's however fast I'm moving towards it, plus the velocity that the sound's coming at me with,
Which is V minus.
and then minus the velocity of the source. If
Yeah.
you follow all that? And then this is going to be over the wavelength I'm seeing right here. For the scenario I set up, then we're doing lambda in the back. If we would have been in front of it, then that would have made this positive, and then would have made the one down here negative, and it turns out it's going to come out the same. Okay, but following the scenario that we have written out here, now I need to rewrite this way. Because I want to get my frequency in terms of your frequency, using this fact.
Right.
So if I'm going to divide by that, that's the same as multiplying by this thing's reciprocal.
Mm-hmm.
So that is going to be f sub L is equal to f sub S comes to the upstairs, times V sub L plus V minus V sub S, all over V plus V sub S. Let me see how exactly they have the equation written. There's got to be a way for us to get from where we are to where they are.
You don't have a V sub S in the top.
Oh my goodness. I'm so dumb. Okay. When you emit the sound, the fact that you're going this way does not change how quickly the sound wave comes at me.
Oh, yeah.
Duh. We already had that conversation. Okay. So, one sec. So, that does not show up here as part of the velocity of the wave. Okay, so back to this, and that's just y sub b, or lambda sub b. Good?
Yeah.
Okay, and so there's how it actually comes out. So f sub L equal to f sub S times velocity of the listener plus v over the velocity of the source plus v. Good?
Yep.
Okay, and then they don't bother writing the wavelength version of the formula. But, so here's what it is in general. Turns out, doesn't matter if you're talking about the front and the back.
Okay.
All right. So there's Doppler effect.
Cool.
Okay. Dude, chill. We're lecturing.